right. It says it's live. Hello, world.
Good morning, good afternoon, good evening, everybody. Ben, could you advance the slides to our second slide, please? Thank you. Thank you, everybody, for joining. It's a real pleasure to launch the second Learning for Dynamics and Control L4DC 2020. And I want to thank everybody for your graciousness and your willingness to participate and your participation in this online format. We'd like to start with some technical details on how to connect. I think many of you are now connected. It looks like we're live. But we have some details here. There are two main components to L4DC. There's the online live talks, and there's the posters and all of the papers associated with L4DC. So for the talks, the links are available on our website, l4dc.org. And in order to interact and ask questions of the speakers, you must log in to YouTube directly or log in through your Google account. You can ask questions of the speakers in real time, and these questions will be logged in the YouTube chat. We have moderators who will collect the questions. Unfortunately, we only have a few minutes for questions for each talk, but we will collect the questions, and there will be a discussion available. For the posters, you can go to our website, l4dc.org, and click on the poster session via open review. And you can view posters, the papers, and open up chat discussions with the authors. We'll keep the link for the poster session for 2 weeks after the conference is over. I'd like to thank all of our invited speakers. I'd like to thank our contributors. I'd like to thank our sponsors, Bosch, Merle, MathWorks, and TRI. And we have some very short promotional videos from some of our sponsors, which we'll be showing in the breaks. I'd also like to thank ONR and NSF for their continued and foundational support for this conference. Through L4DC, our goal has been to create a forum that brings together pioneers and state-of-the-art research in the areas of control, optimization, machine learning, and related disciplines, and really state-of-the-art applications in order to create this prestigious annual conference that defines the field of learning for dynamics and control systems. And we feel that a conference on this topic can have a tremendous impact by not only bridging scientifically to somewhat distant areas, but also from a community perspective, nurturing a growing number of junior researchers working on this emerging interface and providing a natural home for professional development for students and faculty. So following the success of the inaugural L4DC workshop in 2019 at MIT, what we're starting now is the second annual conference for learning for dynamics and control. And in the long term, we'd like to sustain this event as an annual conference where the best results on this emerging interface are presented. We aim to create a new community of people that think rigorously across the disciplines, ask novel fundamental questions, and develop the foundations of this new scientific area. So for this year, we formed a program committee consisting of 57 participants from L4DC 2019. We invited submissions back in the fall of short papers addressing the topics of at this interface, and we received 135 submissions. Members of the PC reviewed the papers, and we are happy to say that a set of 14 papers, contributed papers, will be presented orally over the next 2 days, and an additional 85 will be presented as posters. Finally, we'd like to acknowledge all of you for your flexibility in the delay of our conference by 1 day, from Wednesday to start today and to go on to tomorrow. This is in order to acknowledge the need to transition to a real commitment but to removing anti-Black racism in academic institutions and STEM specifically. So with those opening comments, we'd like to begin the conference. And so I'd like to move to our first invited speaker and to move to the introduction of our first invited speaker.
Yeah, so welcome everybody. It's a pleasure today to introduce our first speaker, which is Professor Karen Wilcox. So Professor Wilcox, she's a chair professor of aerospace engineering and engineering mechanics at UT Austin, where she's a director of the Oden Institute for Computational Engineering. So Professor Wilson got her master's and PhD from MIT. Then she went on to Boeing Phantom Works for a year. And then she came back to MIT as a professor, where she spent over 15 years in the Aero-Astro department. So Professor Wilcox is a world expert in uncertainty quantification and model reduction, or perhaps more generally, computational engineering and scientific machine learning. She received many, many honors and served in a number of leadership positions. She asked me not to make this too long, but in particular, she was associate department head while she was at MIT, and she's now the director of this big Oden Institute specifically for computational engineering. Without further ado, Karen.
Great. Thank you very much, Pablo. So if you can stop sharing, I can try to share. Okay, you can see the slides? Yes, good. All right, well, it's great to be here, at least virtually today with everybody and share some of our work in predictive digital twins. Before I get started, I want to acknowledge the folks who have contributed to the work that I'll show you today, and especially call out my PhD student who is still at MIT, Michiel Kaptein. And what you're going to see today is mostly Michiel's PhD work. I also have Stephanie Salinger, who's a student with me at UT Austin, who's working on the experimental components of this work. And this is a collaboration with Dr. David Knezovic, who is CTO of Excelis. We're working with Excelis on the reduced order modeling and the building of the digital twin. Okay, so I want to do two things in the talk today. First, talk about what is a digital twin, both from the perspectives of use cases and from the perspectives of the mathematical foundations. And then second, I'll show you some of our work that's moving towards creating predictive digital twins using a combination of reduced order modeling and interpretable machine learning. So let's start with the basic question, what is a digital twin? And I want you to imagine a physical complex system, so something like an aircraft. And I want you to think about how that complex system evolves and changes throughout its life cycle. So from its concept through its design, into the manufacturing where it becomes an actual system, into its operation, and then post-life and retirement. And a digital twin is an evolving virtual model of the system that follows the physical asset through its life cycle. So it's not a generic virtual model. It's not a generic digital model of a 777 or an F-18, but rather it's a specific model for a specific 777 or a specific F-18, a model that's assimilating data from that particular asset and again evolving and changing to support the asset throughout its life cycle. This concept has been receiving a lot of attention in the last especially 8 to 9 years in the aerospace community. A lot of the attention has been around applications in structural health monitoring, in sustainment, and in predictive maintenance. But the last few years have seen a real broadening of the use cases for digital twin, both within aerospace and now also stretching to many domains outside of aerospace. The definition that I'm showing up here was proposed by the AIAA subcommittee at the recent SciTech meeting that took place earlier this year. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of an individual or unique physical asset, is dynamically updated with data from its physical twin throughout its life cycle, and informs decisions that realize value. So you see the 3 key pieces there. The fact that this is a model, again, tailored to be specific to a particular asset. Think of it like a patient-specific or an asset-specific model. Second, that it's dynamically updated with data throughout the life cycle. And third, that it's used to drive decision-making. Now, I mentioned this time horizon of 8 to 9 years, and that statement's based on some key papers that came out around the 2011-2012 timeframe from the Air Force and from NASA that really brought the concept of the digital twin to the forefront. But the idea is much, much older than that. And in fact, many people point to the Apollo program as being the place where digital twins were first put into operation. And that was through NASA using simulators, twins, digital twins, if you like, of spacecraft, keeping these digital twins on the ground while the spacecraft were put into space. And this use case, this became very critical and very useful in the Apollo 13 crisis, where, and I'm sure many of you have seen the movie and are aware of that. But during that crisis, the NASA mission controllers were able to take data from the actual physical spacecraft that was crippled and was in space, take the data, feed that data into the simulators that were on the ground in Houston, update the simulators now with this new real data to update them to recognize the changing conditions of the spacecraft, and then use those now data adapted simulators to run all kinds of scenarios and ultimately design the strategies that brought the astronauts back safely. So that kind of sets the stage notionally for what is a digital twin and what some of the use cases might be. And clearly it's a very exciting concept and one that could provide a huge amount of value in terms of being an underpinning for intelligent automation and decision support across many, many systems. But now I want to talk a little bit about what a digital twin might be mathematically. And I want to use the language of dynamics and control. So we could think of our physical asset, our physical twin, as having a state. And I'm showing that here, denoting the state with S. What I'm showing here is the state at different discrete points in time from S0 at t equals 0, S1, and so on. Now, to many people who come from a dynamics and controls background, you might think of the state as being something like position and velocity of an aircraft. And that's certainly a part of the state. But I want you to think of the state as being much, much more than this. Remember our definition of a digital twin, something that is going to mimic the structure, the context of a complex system like an aircraft. And so this state is, for example, may need to represent the geometry of the aircraft, thousands or even millions of parameters that describe the geometry of the aircraft. And of course, those parameters are going to change throughout the life of the aircraft as it goes from design into manufacture, into operation, and the geometry may change with modifications or with wear and tear. The state of the system may also need to contain information about, for example, the structural health, the structural properties of the vehicle. So again, thousands and thousands of parameters that need to evolve and need to represent the structure of the vehicle, or its engines, its propulsion system, the state of its batteries, its sensors, its actuators, and so on. So you can immediately see how to build a digital twin of something like an aircraft, we're talking about a very, very high dimensional state that is complex and contains information that cross many spatial and temporal scales. So we can also now think about defining the digital twin state, and here that's denoted by D sub T. And perhaps one important thing to note is that the digital twin state, depending on the use case, clearly does not necessarily have to embody everything that we could imagine in the physical twin state. And that in itself, defining the digital twin state and tailoring it to particular use cases is itself a very interesting and open research question. And then, of course, the familiar assimilation task, it says to take observations, here denoted with O, from the physical asset, and use those observations to drive inference and assimilation to infer the digital twin state. And again, keep in mind that the amount of data that we can collect from the physical twin, the sensors that we'll have available, means that at best our state will be indirectly observable and partially observable. We denote here with U the control actions. So these are actions that could change the instantaneous state of the system directly, or they could be actions that change the operating conditions of the state that in turn induce change the operating conditions of the vehicle that in turn induce a change in the state. These control inputs could also be actions that influence the data that we're able to collect. And again, that could be instantaneous. So taking an action to perform an inspection, or taking an action to perform a diagnostic maneuver so that the vehicle goes into a state that yields data that may be more informative towards the inference problem. Or they could be actions that lead to information in the future. So for example, an action that says you're going to need a new sensor, design, deploy and install a new sensor. We'll also define reference observations denoted here with O hat. So these are observations that we can generate by simulation using our digital twin. In other words, these are predictions of the observed data that we can make by running our digital twin models. And to formalize the task of determining actions that are optimal with respect to some metric, we can define the notion of a reward denoted here by R. So, and then perhaps the last point to make is, of course, one of the powers of this framework is that we can now use the digital twin to issue predictions out into the future for times that go beyond the current time where we may have data, and use those predictions in support of decision making. So as I've presented it here, this may look like a familiar estimation and planning problem to many of you. And in fact, one piece of Michael's PhD work is to cast the digital twin problem in the setting of estimation and planning, because we believe that many of the tools that are used in estimation and planning are clearly going to be very valuable and very relevant here. But I want to draw out three key pieces that to emphasize that I think really start to distinguish what is it about a digital twin that goes beyond the kinds of problems that are typically seen in estimation and planning. So the first is the complexity that I've already alluded to. We are potentially talking about states here that are in the thousands, if not millions, if not billions of degrees of freedom. Extremely complex state spaces, again, crossing multiple scales across space and time. And we have to be able to get a handle on the complexity of that problem to make the inference, assimilation, prediction, and decision tasks tractable. And as you'll see in a second, what we propose is to bring physics-based models as a lens through which we can start to make those tasks tractable. The second point I want to make is the importance of uncertainty. So of course, uncertainty is pervasive and is a critical element of absolutely every single piece of what we see on the slide here. It's essential that uncertainty is accounted for as we again perform those tasks of inference, assimilation, prediction, and decision. And of course, that makes the problem and the complexity of the problem we have to solve even more challenging. And then the third point is that I really want to emphasize that this is not a problem that we can solve today. We can formulate this problem, and indeed that's, again, something that Michael's taking on in his PhD work. But to actually solve problems at the scale we need to be able to solve them to create something like a digital twin of a full aircraft goes well beyond what we have in hand today. We can use these mathematical foundations, but then we really need to think about algorithms that are robust, that are interpretable, and that are efficient and scale, again, to the complexity of the problems that we need. And I'm going to show you in the next part of the talk some of the steps we're taking towards achieving that using, again, the lens of physics-based models and reduced order modeling. Okay, so at the heart of our approach is the need to combine data-driven learning with physics-based modeling. And that's one way we see to really start to break the complexity of what is otherwise a completely intractable problem. The particular use case that we're thinking about is enabling a self-aware aircraft. So the idea of a self-aware aircraft is that it's a vehicle that can sense structural data, so it can read sensors from on board. It can use that data to estimate its structural state, so estimate its health at any given instant on any given day. Can then use that updated estimate of its state to update its flight capabilities, so determine, today how fast can I fly, how tight of a corner can I turn, and so on. And then with those updated capabilities, dynamically replan the mission. This use case of self-aware aircraft clearly has relevance to many different applications. As just one, we can imagine that this would be very important to have autonomous health monitoring and dynamic mission replanning for package delivery drones that may be operating in urban areas in the future. So clearly a digital twin can be an enabler for this kind of concept. A digital twin can enable big decisions. And these decisions are big for two reasons. They're big because they're very complex. We've already talked about the complexity. But they're also big decisions because they're of high consequence. We're talking about decisions that involve situations that literally put people's lives at risk. And so for those two reasons, both the complexity and the high consequence, it's really not feasible. I think actually it's quite hopeless to think about driving those kinds of big decisions with methods that are built only on data. These big decisions need more than just big data. They need big models too. And by big models, what I mean are physics-based models, physics-based predictive models that are representations of the laws of nature. These are models that innately embed the concepts of time, space, and causality. And by doing that, these models define low-dimensional manifolds in what are otherwise absolutely vast, sometimes even infinite dimensional solution spaces. So the physics-based models are a lens through which we can look to start to bring some tractability to this otherwise intractable problem. The models also bring in predictive power by, again, encoding the laws of nature, encoding the physics. The models give us a window to start issuing predictions about conditions we haven't seen, conditions we have no data for, conditions that we never want our systems to get into. These models can bring interpretability because they operate in physical quantities that are very familiar to engineers and to decision makers. So these big decisions that we have to make have to bring in the predictive power, the interpretability, and the domain knowledge of the physics-based models and put that together with the power of learning from data. And to achieve something like a predictive digital twin and tackle some of those use cases I talked about, absolutely, it's absolutely essential to bring together these two perspectives, data-driven learning together with physics-based predictive modeling. And in the next part of the talk, I'll show you just a glimpse at some of the methods that we are working on to achieve that vision. And in particular, you'll see how we're using component-based reduced order modeling together with interpretable machine learning. So we already talked about benefits of physics-based models in bringing in these physical laws that define these low-dimensional manifolds in vast solution spaces, and allowing us to simulate unseen scenarios and generate simulated data for conditions that we don't want our vehicles to get into. For giving us a window on understanding uncertainty and confidence and predictions that are used to support decisions and being interpretable through working with real-world quantities. Now, of course, the catch is that these physics-based models tend to come to us in the form of partial differential equations. And to solve those partial differential equations, we have to numerically discretize them. And what we end up with are big, literally very big numerical models that we can solve, but take timeframes on the order of hours or maybe even days, even with high-performance computing to solve. So those physics-based models manifested as numerical solution of PDEs are too complex and too expensive for use in a digital twin setting, which demands much more than just 1 or 2 runs, but rather running a physics-based model many, many times in support of inference, in support of uncertainty quantification and control. And it also sometimes demands that we run these models in near real-time settings, perhaps on board a vehicle. So this is where the mathematical approaches of model reduction come into play. And I'm not going to go into any details in this talk, but just say at a very high level, the notions of model reduction, and in particular, projection-based model reduction. The general idea is that we have our physics-based model over here on the left. This is what we get when we discretize the partial differential equations. We get a big model that may have thousands, millions, billions of degrees of freedom. And again, one solution of that model may take hours or even days. And what's model reduction? We want to mathematically extract a lower dimensional model, so a model that has dimension on the order of tens or hundreds that can be solved much, much faster. And again, without going into the mathematics of how it works, there are 3 main steps in projection-based model reduction. The first is a training step where we need to query a large system, solve these PDEs to generate training data over representative scenarios. The second step, we identify low-dimensional structure. And in what I'm going to show you today, we're working just with a linear basis that defines a low-dimensional subspace in the high-dimensional state space we started with. And then the third step, and the third step is really key, which is to get the reduced model, we take the PDE model, we take the physics-based model, and we mathematically project it onto the low-dimensional subspace that we've identified in step 2. And that projection is absolutely key because unlike other methods, and particularly machine learning methods for creating surrogate models, the projection, even though the reduced model is a mathematical abstraction, the projection embeds the physics in the reduced model. And in doing so, actually gives us a way for many systems to be able to bet theoretical guarantees on the performance of the reduced model, to be able to guarantee that we can preserve important properties like stability, in many cases to be able to derive error estimators and so on. So reduced order modeling is key. It leads to low-cost physics-based models that are an enabler for predictive digital twins. But creating a reduced order model of a full vehicle is itself a major challenge and actually really goes beyond a lot of the state-of-the-art in methods. So it's on this aspect that we're collaborating with Axelos. You see here on this slide some of the challenges that we have to overcome with the expensive training step of scaling to these very high-dimensional parameter spaces that I talked about, of dealing with things like discontinuous parameter space. And again, without showing you any of the mathematical details, the approach that we use is notionally divide and conquer, which is to say take a complex system that has many, many parameters, break it into pieces, derive reduced order models for the pieces separately while accounting for the interactions among the pieces, and then put them back together to get a system model. Again, I'm not going to present any of the math for doing that, but just to tell you that mathematically this is built on the theory of static condensation or substructuring that comes from the finite element community. And I think it's a very powerful set of techniques that, again, using decomposition of a complex system as a way to tackle some of the curses of dimensionality. So putting this together, again, now that's armed with these component-based reduced models, we have an offline phase. This is a phase that takes place on the ground with all of our supercomputers and our high-performance computing resources, where we construct a library of reduced order models that represent different asset states. And again, those reduced order models are all built at this component level. What we then do is to use the library of reduced order models to train a classifier. So because the reduced order models are very efficient to run, we can run many, many, many scenarios with the reduced models, many more than we could run with the original high fidelity codes, and train a classifier that predicts asset state based on sensor data. And then the way we deploy and update the digital twin is now imagine the vehicle is flying. We have a current digital twin that's representing the structural health of our vehicle. We obtain some new sensor data. We can feed that into the classifier very rapidly via the classification, go and grab a new model out of our library, compose an updated digital twin and then use that updated digital twin to drive analysis, prediction, optimization, and planning. And again, I really want to emphasize that even though the reduced models are mathematical abstractions of physics, and for us, this is for the example I'm going to show you, this is the physics of the structural response of the vehicle are absolutely embedded in there through the nature of the projection that we create. I won't have time to talk in detail, but I do want to mention that for the classifier, we are using optimal classification trees. We're using the work of Dimitri Bertsimas and Jack Dunn, where they proposed a very scalable approach using mixed integer programming to train an optimal classification tree. And one of the things I really like about these optimal classification trees are the interpretability that they bring. And in particular, by interpretability, just with this simple example you're seeing here, what you're seeing is taking sensor data and using it to classify the damage state on the wing, on a particular section of the wing. And it's very interpretable in the sense that one can say, okay, we got classified into our most severe damage state. Let's go back and look at the sensors that led to that decision and really understand whether how much uncertainty we might have, whether the sensors themselves might be compromised, or again, to drive those actions that might require collecting more data before we make a critical decision. Most of our work is simulation, as Pablo said in the introduction. I'm a computational person, but for this project, we also have a significant hardware component to the project. We have a custom-built Telemaster aircraft, a UAV, that we constructed together with Aurora Flight Sciences. It's got custom wing sets that let us introduce damage and structural modifications into the wings. We also have a custom sensor suite that let us take, we have these sensor stickers that let us take measurements wirelessly. And you can see here just some of our early experimental results where we're showing that with this combination of the models and the sensors that we have on board the vehicle, we are actually very effectively able to classify changing states of the vehicle. So the vehicle was supposed to be flight testing this spring. Those plans have been put on hold a little bit, but we're really hoping to get it back in the air in the coming fall. As part of that piece of it, we're building the digital twin of this particular vehicle. And this is the work that we're doing together with Excelos. And again, the reduced order models that I've talked about at a high level form a really key part of building that predictive digital twin. So we start with a very sophisticated finite element model that represents sort of all the details of the wing. And we're able to create reduced order models that provide very, very rapid simulation capability, fast enough to be able to train, generate the training data for the classifier training and also to execute the predictions online. So very last slide, let me just show you how all of that comes together. If I can get this little movie to play. What we are looking at here is a notional situation where we have a UAV that has to navigate these obstacles here on the left. At this point in the trajectory, the vehicle sustains some kind of a damage condition, and you saw the damage start to appear on the wing. What we're seeing here is strain readings that we're collecting from the onboard sensors, and you see here the classification tree, which is taking those modified strain readings and very rapidly detecting that the vehicle has moved from pristine state into its damage state. And as those classifications are made, what you'll see is that when the vehicle gets to this point and has to make the turn around the third obstacle, it recognizes that its damage state is severe enough that it can no longer make this more aggressive, shorter but tighter turn that pulls higher Gs on and puts greater load on the wing. So it switches to the conservative flight path. And again, this is a simulation, but this is what we're hoping to demonstrate when we get back in the air. So with that, let me stop. Thank everybody for tuning in. And if you'd like to learn more about this work, especially the mathematical details that I didn't show today, you can find much of the work and many of the papers at the website there. Thank you.
Great. Thank you very much for a very, very thought-challenging talk. So we have a few questions. Let me paraphrase perhaps two of them in a single one because they're somehow related. So one of the questions is of how does this kind of digital twin idea interfaces with some of the classical ideas about system identification, learning, MDPs? somehow, I mean, of course, you're building on top of this, but kind of what else is needed, kind of for.
Yeah, that's a great question. And one of the reasons I'm very excited about the notion of a digital twin is that I feel that it's a collision of all the things that so many communities have been working on for many years. Of course, a big part of the digital twin is things like finite element models and CFD models and sort of the modeling and simulation capability that have been at the core of developing aerospace vehicles. But then putting that together with the learning, the dynamics, the controls, the notion that a system has a state, that you can mathematically represent that state and then evolve it over time. So, I think, and this is probably true for many concepts, if you really dig in, you don't necessarily see anything fundamentally new, but what you see is ideas from many corners coming together to create something that I think is a very new way for us, for aerospace engineers, to think about what computation can do and how it can drive decisions in their systems.
Mm-hmm. So let me ask, I think also this other question, it follows on that, and I think it's a very nice connection. So here, Michael Churchill asks, what are the challenge of the sim to real gap, right? Kind of the gap between simulation and kind of what's actually happening. What happens if your models don't actually reflect reality, and how do you take this into account?
Yeah, that's a great question. I mean, of course, the models never reflect reality. And even if you did have a model that could track reality, chances are it would be too complex to use in this kind of setting. So I would say, first of all, I think this is a very interesting open research question. And again, I want to emphasize something I said during the talk, that the vision I laid out, with the probabilistic graphical model, we can't solve that, not even close to being able to solve that today. And there are many reasons why we can't, but the question of model inadequacy, or the gap between reality and model, is a huge part of it. And I think this is a challenge we have to tackle from many different angles. One way to tackle it is to get better models and to make them more efficient so that we can bring more higher fidelity information, and that's kind of the tack we take with reduced order models. But at the same time, that's never going to get us all the way. So we have to think about how do we use data to perhaps learn more about the gap. I think one very interesting use case of the digital twin would be hindcasting. We have something to learn from weather forecasts, who clearly sort of use this notion, they don't call it a digital twin, but in a way, there's a dynamically updated model of a region that is constantly assimilating new data, but then also going back to look and see how forecasts performed on data that's been collected. So I think there's ideas there that can be brought into play, and I'm sure many other things. So this is a really important piece of it. And maybe just the third thing to mention is all decisions are going to be made in the face of uncertainty, and figuring out how we get a handle on that uncertainty and recognizing that our predictions will always be imperfect, but we have to start thinking about risk. What is the risk of a UAV making a certain maneuver? Well, it depends on its context, where it's flying, what's on board, and how you incorporate all of that and ultimately just make the very best decisions that you can.
Mm-hmm. Great. Thank you very much for a very interesting talk. Again, unfortunately, we don't have time for more questions. I see that people are quite interested, and we have a few more questions coming. So I would encourage everybody to go to the open review site. You can in there establish a two-way conversation with the authors of the paper. So thank you very much, Karen. That was really great.
Thanks, Pablo. Thank you, everybody.
Alex.
Hi, this is Alex Bine here from Berkeley. Again, it's our real pleasure today to welcome you, and we really want to acknowledge our sponsors. Without their generous support, this organization of this year's conference and next year's conference would not have been possible. We're really excited. Our sponsors include Bosch, Merle, MathWorks, and TRI. We also want to acknowledge the ONR and NSF for their contributed support. Hopefully next year at L4DC, you'll be able to meet them in person at the conference, and we look forward to welcoming them next year at the conference. And so this year, as part of our joint association with them, we're proud to showcase you a short video for each of them and we will start with Bosch. So I think I will hand it over to you again, Ben, to switch over the screen.
Hi, we're happy to be part of this first virtual conference on learning for dynamics and control. We at the Bosch Center for Artificial Intelligence are enabling new innovative products by using machine learning technology.
Our task as research scientists and engineers is to bridge the gap between the academic problem settings and the industrial products.
My name is Edgar, and I'm a research scientist at the Bosch Center for Artificial Intelligence. We at Bosch are always concerned with making our production processes better and more efficient. With this machine, we have developed an algorithm based on probabilistic modeling and safe optimization in order to make a milling process more efficient without damaging the machine.
Hi, I'm Andreas, and I'm working at the Bosch Center for AI because I'm fascinated by the possibilities of AI and reinforcement learning in industrial products. For example, this is the Planetics technology. It's a contact-free transportation system based on magnetic levitation. With this technology, we can radically improve manufacturing in cleanroom environments. And only based on clever combination of physical knowledge and AI technology could we achieve the impressive flight performance.
And now, enjoy the rest of the conference.
All right, so we'll be back in about 4 minutes with our first session of contributed talks on learning dynamical systems. So we'll start at 9:15, and so I guess you might as well just stay logged on. And thanks everybody. I'm loving this YouTube chat. Great to see so many people who I recognize on there, even though I know we're all very far apart right now. Yeah, warms my heart. All right, so we'll see everybody again in about 3 minutes.
All right, so I guess I am next. And Tassos, you're around?
Hello.
Okay, all right.
Karen, thank you very much.
Yeah, Karen,
was
that was
great.
great talk. Yeah.
It was awesome.
Okay, good. I just saw all the chat thing. There was a bit of an echo. Hopefully it was clear.
It was just a small echo. You could understand everything you were saying, but I was concerned there was something on our end.
Okay, so we have the three, I see three of the speakers, Tuhin, Namhi, Bachir, you're all online.
Yes.
And
Hello,
is there
everyone.
someone from, is Max or Joshua online? All right. We need, hopefully they know that today is the day. So
I will send them an email.
Okay, so the way this is going to work is I'm just going to introduce everyone, and I'm just quickly introduction. You give your presentation, 12 minutes. Tassos is going to be looking at the chat for talks on YouTube. He is going to ask you 1 or 2 questions, and I'm going to be keeping time, and we switch to the next talk quickly. And then additional questions will be posted on Open Review, and you should go there and answer additional questions. So that's, we have 1 hour, and we have to really respect the time here. So.
the right one? Yeah, this is the right one. Namhee, if you were there, actually, it would be great if you could just take over the screen share. Could you try that?
Sure. Let me go ahead and do that. Oh, you need to stop sharing the screen first.
Absolutely.
Yes.
Go ahead.
Thank you. Hope this is what I am. Just a second, I'm using a MacBook and it is very high maintenance about using Zoom. So
I know the feeling. It's okay.
yeah, I'll have to reconnect just to let the Zoom share my screen and stuff.
Okay.
I'll be
We'll
back.
wait. We'll wait. Now back here, you're live on YouTube. We'll get it going.
Am I?
Great.
All right. Good morning, everyone, or good afternoon, or good night to some of you. It's my pleasure to be the session chair for the first session of contributed papers. Last year it was only Vita Talks. This is the first year we actually have contributed papers. 10% of the contributions were selected for orals. So the first session of contributed talks will focus on dynamics learning. We have 4 great talks. The first talk is going to be on learning to correspond dynamical systems, and it will be given by Namhee Kim. If you have questions, please post the questions on YouTube chat, and Tassos Tsiamis will be moderating that discussion. He'll be asking your questions live to Namhee. Namhee, go ahead.
Namhee, I think you're muted.
Hello, can you hear me now?
Yes, go ahead.
Okay, so I want to begin my talk by discussing the notion of correspondence. When we have different observations A and B in separate domains, but they actually regard the exact same object in some latent dimension, we say observations A and B are in correspondence with each other. So we're adopting this view in the domain of dynamical systems. So we might observe 2 different bipedal locomotion systems, such as the humanoid walker and this ostrich walker. But if these 2 are sharing the essence of bipedal locomotion task, then there exists a canonical dynamical system that captures these similarities. So our assumption is that these walker characters are just different modalities of the canonical system. Now, this is kind of connected to Karen Wilcox's talk. If we have complex control systems, there exist solutions that can encode these states of complex systems into a much simpler state in the canonical system. And then we can apply control here and then output, decode the output back into the original domain to achieve control in the just steps of simple reductions. And then moreover, we can do this over different characters, essentially allowing us to follow these arrows to match the motions and control schemes of different characters as long as they share the characteristics through these canonical systems. However, these require mathematical and handcrafted solutions, and our contribution is to propose a method to replace these analytical canonical systems with learned canonical systems, introducing autoencoders, which will enable us to further introduce arbitrary characters to be corresponded with one another. So to apply our method, we are treating these dynamical systems as generators of trajectory data. So we are having pairs of current and next states, which are the results of running these systems forward in simulation. And then we apply our learning pipeline, which is as follows. So as I said, there is a notion of current and next state, which are paired for simulating these systems. And we are going to apply autoencoder to the current time step state and the next time step state to get latent states of the current and next time steps. Now these two are linked via what we call the latent forward dynamics model. And this one is unsupervised, but this introduces temporal structure into the latent factors that are forming in this autoencoding. We can repeat the same thing for different systems. So system A and system B are both projecting their states onto a latent state space. And then what we want to do is make sure these two states are living in the same topological space within these latent dimensions. Now I provide an overview of loss functions. So first of all, we are going to use autoencoder loss, which is already very prevalent in the deep learning literature. So as to honor the original state distributions that are present in the latent dimensions. Now, what we want to do is to make sure system A and system B are sharing a similar neighborhood inside the latent dimensions. And what we do is use this symmetric nearest neighbor loss as an approximation to distribution-wise distance as to fuse the distributions of sources A and B together in the latent dimensions. Moreover, we enforce forward dynamics consistency using the model that we introduced here so that although unsupervised, the latent states of the current time step and the next time step are following some kind of temporal structure. So here's a sneak peek of the result in our learning pipeline. So after training, we are left with this state space, which I visualize using PCA. And these blue arrows are indicating the output of latent forward dynamics predictor computed over a grid of points. And you can see the latent factors that are outputted from learning here is forming a dynamical system in its own right. And there exists a limit cycle that the state is following. Moreover, the motion is not actually completely limited to the limit cycle here, because when some perturbation happens and the state gets knocked out of the limit cycle here, the forward dynamics that is in place is going to essentially nudge the states that are diverging to converge back into the limit cycle. We'll touch upon this point when I look at the perturbed state mapping. So we are providing a proof of concept by matching these three control systems. And as a result of putting these three systems into correspondence, we will get a latent canonical control system. And the successful correspondence would make sure that the gate cycles of these different characters to align with one another. But these cycles don't have to align in a unique order. It can be sensitive to randomization. As I said, the latent forward dynamics model can be unsupervised, and depending on the random initialization, the pattern of correspondence can look slightly different. Lastly, we want to point out that these are going much further than simple matching of limit cycles, and we want to make perturbations of these systems to observe whether the limit cycles are going beyond just a simple matching of circles, and we are incorporating notion of recovery and control in our correspondence scheme. So here's the result. And on top, you see physically simulated states that are actually experiencing control in a physically simulated environment. At the bottom, you are seeing just pure visualization. So these are actually not physically simulated. These are just visualizations of the correspondence states. So when I am swinging this pendulum at a certain frequency, and then I am using the arrows that we've seen to project the states of this pendulum to the latent dimensions, and then I am projecting those latent states to the original system, which is this Walker character, then we see that the swinging of the pendulum is matching with the complete walking cycle of this Walker robot. And this correspondence goes in both ways. What's notable is that the imagined states are visually plausible, although the motion is based off of a completely different character. And then this goes for all of these three pairings. As I mentioned, the matching of our controllers don't have to be completely unique. So depending on what kind of random seed we're using, different mappings can occur, and that is fine because we do not have explicit notion of phase that is exposed in the learning pipeline here. But you can see that when this ostrich robot is extending its purple leg, it doesn't have to be the purple leg for the Walker character here, but it is also extending one of its leg at the same time as to match the timing of the foot stroke. So overall correspondent patterns are looking pretty similar. Here we visualize perturbations to the simulated characters and how that visualizes in the imagined states. So we're throwing boxes at our simulated characters to introduce some forward and backward pushes to its center of mass. And then, as you can see, when the ostrich walker goes through perturbation, the imagined states are also going through perturbation, and the same can be said for this humanoid walker and the ostrich walker. And this is essentially showing that the perturbations and the recovery from these perturbations are also taken into account, which goes much beyond just simple matching of limit cycles. In the paper, we also provide quantitative analysis using simple linear models to assert that these correlations are statistically significant. This corroborates with our diagram earlier, where different perturbations may knock the state trajectory outside the limit cycles, but the forward dynamics that is in place is going to nudge these diverging states back to the limit cycle. Just note that the limit cycle and the forward dynamics are learned based on the limited support of simulated data. So outside the support, these predictions are going to be mostly extrapolative, but we can see that within the support of the data, the system is showing pretty stable patterns here. In the paper and the supplementary video, we supply quantitative and qualitative ablations as to show that removing any of the learning components can result in invalid mappings. Now, we want to discuss some extensions of this work. So right now, we are investigating on how to leverage these learned canonical systems to boost efficiency and speed in reinforcement learning. So one key idea to do that is to incorporate encode, control, decode 3 steps by encapsulating correspondence inside the policy. And the current schematics that we have is to encapsulate this pre-trained canonical dynamics from the previous figure inside a policy as to provide essentially some bootstrapping in our canonical in our reinforcement learning framework. And then to do so, we need to maintain this learned dynamics and distribution about the latent states inside the policy. And then we can potentially design the reward function that is based on the distribution matching as to train an encoder and decoder to boost the efficiency of the learning of a controller for a novel system. Another interesting thing to investigate is how to achieve this correspondence across characters that are much less similar, but are still following essentially the same principles of locomotion. So this elephant character might have really large gaits, but walking at very small frequency. And then this mouse character might be making very fast, very fast and high frequency gaits, but at a much smaller gait. So how do we match these two motions together by learning the latent canonical system? Is to perhaps expose the character parameters into the latent dynamics function as to make this function generalizable to arbitrary characters, essentially following the same principle of locomotion. Another thing is to look at the same character who's performing different gaits. So maybe we are looking at a walking gait that's resulting from corresponding walking characters together. And then I imagine if we match running characters together, we can achieve latent dynamics function for a running character. So how do we make sure that these latent state space can be shared across different gaits and different tasks? My proposition is to enter goal parameters into the latent dynamics function so that the latent dynamics is generalizable to different tasks and different gate patterns. Now I'll summarize the work. We are using autoencoders with distribution fusion and latent forward dynamics to learn correspondence across dynamical systems. As a result of this correspondence, we are gaining a latent canonical system which may replace handcrafted reductions that is often used for control. And lastly, we are hoping to leverage these latent canonical systems to increase efficiency and speed in reinforcement learning by enabling transfer learning via learning by analogy. Thank you, and I'd be happy to answer questions.
Thank you very much, Namhi, for a wonderful talk. We have some questions. Tassos, you want to take it?
Yes. So one question is if the stability of the system can be analyzed using these latent variables.
So can the original systems be analyzed using the canonical system? Is that the?
So I guess about the, let's say, the property of the original system,
right?
Which is like stability, for example, if this can be analyzed in terms of the latent space.
I believe there is some loss of, I guess, resolution happening when you learn these correspondences, and usually these canonical systems are, lower in dimensionality. So in terms of, being able to analyze perfectly the original systems just using the latent systems, I don't believe so.
Okay.
So there's another question. Is there time or?
What last question before we move to the next?
So another question online is, how is it possible to, if it is possible to correspond between different time scales? For example, we have a slow and a fast walker.
Yes, so that is very similar to what I have shown here. So, the elephant and the mouse, they don't have to be walking at the exact same frequency. So essentially, capturing the character parameters, including the timescales, would be appropriate for learning a generalizable controller that, that generalizes over for varying timescales.
Great. Thank you, Namhi. I'd like to end the discussion for this talk here. You can continue the discussion at Open Review on this paper, as well as all other papers. I'd like to introduce the next talk now, which is focusing again on learning dynamical systems, but this time using side information. And the speaker will be Bachir Al-Khadir, joint work with Ali Ahmadi at Amir Ali at Princeton.
Thank you very much. Can you hear me?
Yes.
Okay, great. Well, hello, everyone. First of all, I would like to thank the organizers for tremendous effort organizing this conference and making it possible for me to be here online with you. Today, I want to talk to you about learning dynamical systems with side information. So let me just jump right in and present the problem to you. So I'm interested in the following continuous time, autonomous, dynamical system given by the equation x dot equals f of x. F is a function from Rn to Rn that I call a vector field. And of course, for example, in dimension 2, you can plot this vector field. And it will give you a plot like this one. I'm going to assume that this vector field is unknown to me, so I don't see it. And I'm going to try to learn it from on a compact set, let's call it omega, from a bunch of trajectories. Okay, for example, trajectory 1, trajectory 2. I'm going to be in the setting where the data is scarce and noisy. More specifically, what I have access to is a bunch of measurements on these trajectories. Xi, which is a measurement of the state space, and Xi dot, which is a measurement of the time derivative of the state variables. I'm going to assume that both of these could have noise in them. Okay, so these are noisy measurements. And since data is limited and noisy, I need to exploit side information. And side information really means anything you might know about the system, ranging from common sense, some domain-specific knowledge, some laws of physics, etc. And whenever I bring in side information in this talk, I'm always going to call upon this guy, the side information guy, who's going to present the side information to you. So mathematically speaking, okay, a side information could be the knowledge that the dynamical system has some equilibrium point, okay? Or it could be that I know of some set that should be invariant for this dynamical system. It could be that I know of two sets, A and B, such that trajectories that start in A never reach B, for example. And you get the idea, you know, like another side information would be the knowledge that some energy decreases with the system. It could be that you know the sign of the derivative of the state variables on some regions of the space. It could be that you know that some components of the vector field are monotone on some regions of the space, etc. Here is our plan of action. I'm going to take this data, okay, and I'm going to fit a polynomial vector field to this data, to this noisy data that I collected from trajectories, simply by first writing this least squares problem. So when I say polynomial vector field, what I mean is that I have a vector field, a candidate vector field that I'm trying to learn, whose entries are polynomial functions of the state variables of some fixed degree. And the coefficients of these polynomials are the decision variables of my least squares problem. And I'm going to show you how to use SOS, or sum of squares techniques, to impose this side information on my candidate vector field. I'm going to show you how to add additional constraint to this least squares problem to enforce any side information you might have. And I'm going to try to be as concrete as possible in this talk. So what I'm going to do is present to you two examples that show the added value of side information. The first one is from epidemiology, and the second one is from physics. In the long version of the paper, we also study an example from biology, and we have some extensions to control. So let me show you the first example, and this model was proposed in the epidemiology literature to it models the spread of a sexually transmitted disease in heterosexual population. I believe it was gonorrhea. So I have two state variables, x1 and x2, and they represent the fraction of infected males/females in this population, okay? And the dynamics for males, for example, is given by the following formula. The first term that I have here represents the recovery rate, and the second term represents the infection rate, okay? And I have a similar equation for females as well. Said differently, now I have a vector field in dimension 2. And now I can plot it for you since it's in dimension 2. And I'm going to take the following values for these parameters AI and BI, okay? And the plot is going to look something like this. So I'm going to assume that I do not know these parameters AI and BI. Not only that, I'm going to assume that I don't even know that the vector field has this special structure. The only thing I'm supposed to know is one trajectory, or to be specific, 20 noisy measurements on a single trajectory. And that's all I'm going to see, and I'm going to try to learn the vector field from that. So this is what happens if I fit a polynomial of degree 3 to this data. I get this least square solution that tries to do the right thing, you know, around the training trajectory, but is pretty much horrible elsewhere. It does not match the behavior, the qualitative behavior of the true vector field. What can I do to improve this? Well, I can use side information. So the side information guy is telling me, for instance, that at 0, or the origin should be an equilibrium point. Okay, so this is satisfied by the true vector field, but this condition is not satisfied by the vector field I just learned. And this side information simply corresponds to the fact that if no male and no female is already infected, the disease cannot spread. Okay, great. So let's add this additional constraint to the least squares problem I showed you before. Let's solve again and see what we get. So we get the following vector field, okay? And now it satisfies this additional constraint. Its qualitative behavior improved, but we're not quite there. So let's go one step further and use another side information. So invariance. The other side information is invariance, and more specifically invariance of the unit square. So this simply comes from the fact that x1 and x2, my two state variables, are supposed to represent fractions. And as such, they should be between 0 and 1 for all times. I should not have arrows pointing outside of this square. So you might ask, how can I impose this side information on my vector field? And to answer that, let me do a small detour. And let's say you're interested in a set that is defined by a single polynomial inequality. What I'm going to show you is going to apply to multiple inequalities as well. But for the sake of simplicity, let me stick to one inequality. And let me give you a rough sketch of how this thing works. Okay, so how can I impose the trajectories that start inside the set, never leave it? I have to look at all the times I intersect with the boundary. So in particular, at those times, g of x would be equal to 0. And I have to look at the two vectors, f of x, which is the direction I'm supposed to be taken, and gradient of g, which is the rate of increase, which is the direction of the biggest increase of this function g. And the inner product between the two should be in a negative. So this is a necessary condition for invariance. And you can see it has this following form. It's an implication between polynomial equalities / inequalities. Now, I don't have time to go into much details, but I'm just going to tell you that we can impose this kind of constraints systematically using semi-definite programming, which we know how to solve. And this relies on some sum of squares techniques. So now if I go back to the example and I impose this side information, you can see that all the arrows now are pointing inwards of the square. So now the side information is satisfied. But you see now, let's go one step further and see what kind of other side information we can use. And the last side information I want to present to you is monotonicity. So what do I mean by this? For me to explain this to you, actually, it would be simpler. It would be simpler for me to just show you why this learned vector field does not satisfy this side information, okay? So let's fix the fraction of infected males to 40%, okay? And let's track x1 dot, which is the rate of infection per day of males in this population. What this vector field is telling me is that when there is no female that is, or almost no female that is already infected, I should expect about 5 infections a day. Okay, great. Now, if I increase the number of females infected, the vector field is telling me that there should be almost no one infected anymore, no male infected anymore. And this doesn't make any sense. If you have more females infected, they will infect more males, right? So the rate of infection of males should increase, okay? So this side information can be written mathematically as the following polynomial inequality involving derivatives of the candidate vector field you're trying to learn. And again, this is something we can impose via the SOS techniques I alluded to earlier. And if you add this constraint to the least square problem I present before, you get the following vector field. And now you see that we're getting the right qualitative behavior of the true vector field. Let me move on quickly to a second example that everyone should know. This is the simple pendulum. Its dynamics is given by the second order differential equation that you see here, or equivalently by the vector field in dimension 2 that you see over here. So it's a good thing that it's in dimension 2, because now I can give you the phase plot here, which is a plot of this vector field. So it looks like this. Again, I'm going to assume that I do not see this vector field. The only thing that I'm allowed to see is trajectories, specifically 2 trajectories. So I'm going to take this pendulum, I'm going to put it in an initial condition, and I'm going to let go, and I'm going to track, I'm going to start measuring alongside this trajectory. I'm going to make 5 noisy measurements. I'm going to take the same pendulum from a different initial condition. I'm going to let go, okay? And I'm going to start tracking this trajectory, and I'm going to make an additional 5 noisy measurements. So overall, I have 10 noisy measurements. That's all I know. And now to go a little bit faster, I'm going to give you all the side information at once. So what kind of side information you can use for this problem? The first one is symmetry. And this simply tells you that if you look at the pendulum, okay, and you rotate it around the y-axis, the dynamics should not change. So this is the first side information. The second one is that gravity will always pulls you down. So this is something you will know, even though you do not know the exact formula for the gravitational force, you might know that it always pulls you down. So in particular, when theta is positive, since this pulls you down, your speed should decrease, okay? And if theta is negative, your speed should increase so that it always pulls you towards the origin. So that's the second side information. The third side information is the fact that the system is Hamiltonian, and this simply comes from the fact that there is no dissipation of energy through friction with air, for example. So this is the side information. Now, let me show you how this side information helps you learn, okay? So this is what happens if you just solve a least squares problem and you fit a polynomial vector field of degree 5 to the data. Okay, you get this vector field. You add the first side information I showed you. The arrows are going to move, so we're going to get a new solution. And second side information, let's see how the solution improves. And the third one. So by the time I added the third one, you can see that we're getting really the right shape of the vector field. This is the end of the examples. I'm just going to end my talk by presenting to you a theorem that kind of justifies our approach for learning with polynomial vector fields and why our choice for polynomials for learning. So you can think of this theorem as a density result or approximation result regarding polynomials. So for any vector field you're wishing to learn, let's say continuously differentiable vector field defined on some compact set omega, for any time horizon you care about, for any accuracy you care about, if f satisfies any one of the following side information. So I'm going to give you a list of side information, equilibrium points, invariance of a set defined by some inequalities, and there's some assumptions on these inequalities. And then negativity of some components of the vector field on some regions of the space, or monotonicity of some components of the vector field on some regions of the space, or gradient or Hamiltonian structure. So if f satisfies any one of the side information I just listed, then there exists a polynomial vector field such that trajectories of f and this polynomial vector field, let's call it P, remain epsilon closed for all time. And furthermore, P will satisfy the same side information constraint as f, okay? So you might ask, what if I care about more than just one side information? Or if I want a combination, 2 or more side information, okay? Can polynomials do that? So we proved that actually polynomials might fail to satisfy side information if you have more than one. But what we prove is that if you allow for some room of error, which in practice is enough, if you allow for some room of error quantified by delta, and delta can be as small as you want, as long as it's not 0, then there is a polynomial that delta approximately satisfies the side information that f is supposed to satisfy. So I'm gonna, and the last thing I want to say is that all such properties of this polynomial vector field will come with an SOS certificate, meaning that you can impose them using semi-definite programming. And I'm going to end my talk here. Thank you very much for listening. There is a long version of the paper coming soon, probably by the end of the month. And if you want to know more, visit my website. Thank you very much.
Thank you, Bachir. That's a wonderful talk, great results. I know there's quite a few questions on the chat, but we'll allow 2 questions while we also switch. So, Tassos.
Okay, one question is about how does this approach scale with a dimension and how we can select the degree of the monomials. For example, can we go beyond 5 or 6 states?
Those are completely valid questions.
And also right? by including, sorry.
Yeah, go ahead.
And also by including side information, do we make it more or less challenging?
Right, okay. So to answer your first question about scalability. So our method relies on semi-definite programming. So you can solve it for moderately sized programs, okay? But there are known issues of scalability with semi-definite programs. What I can say is that for this specific field that we're all interested in, which is dynamics and control, usually most of the time, the number of degrees of freedom you have in a system you have few. You know, you can have like a robot with 7 degrees of freedom, 20 degrees of freedom. So in all those cases, semi-definite programming can do a lot. Of course, there are challenges when you go beyond that. And there are a lot of recent work that actually tries to address that. If you use special structure that your problem has, for example, sparsity or symmetry, etc. So that was the first part of the question. The second one is about how to choose the degree of the polynomial. And I would say that's a challenging question, even when you remove the dynamics out of it. When you just try to fit a polynomial, to data, forget the dynamics, how large should the degree go? And I will go even further, if you're fitting a neural network, how large should the neural network go? All of these questions are challenging. In practice, there are some heuristics you can use. You can use cross-validation, you can use this type of stuff, but there is not a definitive theoretical answer that can work all the time. And when you add dynamics into it, it's a whole other thing you're adding.
Thank you. I'd like to get us back on schedule as much as that's possible. So thank you again for a wonderful talk. The next talk is going to stay.
Thank you so much for having me.
Of course. The next talk is going to stay on the same thing of learning dynamics, but it will have a more statistical viewpoint. It's going to be given by Tuhin Sarkar, joint work with Dylan Foster and Shasha Rakhlin, learning nonlinear dynamics from a single trajectory.
Hello, hi. Can you guys hear me?
Yes.
Yeah, cool. Thanks for the introduction. So I'll be talking about learning nonlinear dynamical systems from a single trajectory. This is joint work with Dylan Foster and Sasha Rakhlin. So the outline of the talk will broadly follow as first I'll talk about the general problem on how we can learn f star, which is the nonlinear function from our finite data points. A critical theme of this presentation will be the relationship between stability and isometry. To that end, we will define a concept called k-row stability, and we'll show how this k-row stability lends itself to finite time isometry. So, and in general, finite time isometry is quite important in cases where you want to identify parameters of the underlying system. Following that, we'll consider a specific class of nonlinear systems that we call generalized linear systems, and for which we will provide algorithmic results and sample complexity results. So briefly, a nonlinear system is essentially something that evolves as equation 1, which is xt plus 1 is equal to f star of xt plus epsilon t, where epsilon t is not observed and is just known as process noise. Note that the kind of systems that we consider do not have any control input, but our techniques can easily be extended for that case. So xt is a d-dimensional state vector, and epsilon t is the noise. Examples of f star could be just the linear case, where f star is just a matrix, theta star, or the generalized linear case, where you compose two maps, sigma, which is a nonlinear map, and theta star. Finally, for the rest of the talk, we'll assume that epsilon t is Gaussian distributed with variance tau square. We call these systems self-exciting systems, and it is critical that we oops, sorry. Okay. Yes, and it is critical. Yeah, and it is critical that that the noise has this self-exciting behavior. So how do we learn f star from data? The simplest thing that we can do is we have the least squares estimator, which is f hat n, and we minimize this square loss given by equation 2. For the special case of linear systems, we know f hat n has a closed form that is given by equation 3, where the plus sign is just the pseudo inverse, and the summation xi transpose is also known as the sample covariance matrix. And the invertibility of the sample covariance matrix lends itself to correctly identifying the parameter theta star. But for more general F stars, it's unclear if there is tractability, and there are performance issues which we'll briefly touch upon during the course of this talk. So first, we would like to give efficient algorithms for nonlinear systems, and we'll try to understand what classes allow for computational and sample efficient algorithms. Second, an important concept in robust control is that of certainty equivalence. What that means is essentially to bound performance on counterfactual sequences, it is a very good technique to just explicitly recover F star. Our results will focus on generalized linear systems. So given the data, can we learn the generalized linear system? So yeah, going back. So before talking about the connections between stability and isometry, we'll define a special kind of stability called K-row stability. What it means is essentially if there is a map F that is a d-dimensional map, it is K-row stable if there exists a positive definite matrix K and a constant rho such that F in an appropriately defined norm is rho contracting. Essentially, F should be, so there must exist a norm in which F is contracting for all X. And that norm is defined on the positive definite matrix K. A neat thing that follows from this fact, from this is that any K-row stable F satisfies the following property, that F raised to the power K, little k, is decaying exponentially, where the exponent is given by the rho. So K-row stability implies exponential stability. And in fact, it's actually only a sufficient condition for general Fs. It becomes necessary and sufficient for LTI systems, where K-row stability is equivalent to the spectral radius of the state transition matrix being less than 1. So now we'll show how the K-row stability implies finite time isometry. So for that, we define something known as the effective radius, that is R sub k comma rho, which is essentially a measure of how much xi can go away from the origin on an average. So our first theorem is that, like, if F star is K-row stable, then as long as n exceeds a certain predefined threshold, we have with high probability that the average sample covariance matrix satisfies this kind of an isometry. So it's upper bounded by some constant times identity, and it is lower bounded by some other constant times identity. So what it means is with high probability, the sample covariance matrix is invertible. So one caveat here is this result requires the Gaussian nature of noise. And we say Gaussian in quotes, we only need like isotropic behavior of the noise. So the proof has essentially 2 steps. To prove lower isometry, we simply need a weak upper bound on the sample covariance matrix. And that we can obtain just using the Markov's inequality and get like a weak lower bound, and that automatically implies lower isometry. Once we have that, once we have a lower isometry, we can remove the 1 over delta factor using self-normalized Martingale inequalities. So there's a kind of synergy. We need stability to show lower isometry. Once we have lower isometry, we can show upper isometry. So now we we come back to generalized linear systems, which are given by F star is equal to sigma composed with theta star, where sigma is a d-dimensional map that is applied coordinate-wise, and sigma sub I is non-decreasing. It's 1 Lipschitz and satisfies sigma I of 0 equals 0. Examples of such sigmas could be the sigmoid, the identity, or the ReLUs. So what does K-row stability mean for GLS? So when so k-row stability essentially is given by the following criteria. If theta star transpose k theta star is upper bounded by rho times k, then the GLS is k-row stable. So now that we know what k-row stability means for generalized linear systems, we quickly go into the main algorithm. So our algorithm can be thought of as a form of pseudo gradient descent. It is essentially we update our parameters by a scaled pseudo gradient. So the pseudo gradient is given by equation 4. You can see this is essentially like the gradient, except that in a gradient, xi transpose would be replaced by sigma prime xi transpose. So then the algorithm is simply updating our parameters with this pseudo gradient. One key difference is that we have two options to choose from on which on how to pick our theta hat parameter estimate, and the reason is when sigma is not strictly monotone, we can usually not get a parameter recovery bound. Instead, we'll only get a prediction error upper bound. So in that case, when sigma is not invertible, we randomly select from the different iterates of theta. On the other hand, when sigma is invertible, when sigma is strongly monotone, we have option 2, which is essentially picking the last parameter estimate. Our algorithm can also be seen as a variant of the GLM-Tron algorithm. And so for the case when sigma is not invertible, we have a slow rate, which is that the prediction error lower bound is up. The prediction error upper bound is given by square root d square over n. Recall that d was the length of xt, and n is the number of data points. On the other hand, if we know that sigma is invertible and call zeta as the coefficient of monotonicity, then we can get like a strong parameter estimate upper bound, which scales as d square over n. So the proofs in both cases require isometry property, and then it's followed by a self-normalization argument. So essentially, we have two rates. One is for the strictly monotone case, and the other is for the not strictly monotone. We see that the strictly monotone case is exactly equivalent to the work of Sarkar. However, our toolkit relies only on martingale and self-normalization arguments instead of mixing time arguments. One thing before I end my talk, it is the case of ReLUs. ReLUs are important for RNNs and things like those, and so and they come up in RNN identification. What we see is that even for ReLUs, we can recover parameter estimates, and it is of a similar nature as for the invertible sigmas, just that the coefficient of monotonicity is replaced by an effective coefficient of monotonicity given by e raised to the power minus 2 rho rk rho. So in the paper, we discuss connections between isometry and Lyapunov stability. We give efficient algorithms for parameter recovery for GLS, and our analysis techniques can possibly be extended to a more general setting. Thank you.
Thank you very much, Tuhin. Thank you for a wonderful talk. Tassos, any questions?
So one question is about theorem 1 and asks, why does it not depend on the 1 over 1 minus rho?
It does depend on 1 over 1 minus rho. And the way it depends on 1 over 1 minus rho is through the effective radius. So the only requirement comes in on how large n needs to be. So it only depends logarithmically. So it doesn't depend on the isometric bounds, rather only how large your n needs to be.
Another question is about how you can compare this stuff with overparameterized neural net stuff.
So I guess like then in overparameterized case, D is very, very large. So in that case, we'll have to, I guess, we'll have to impose certain sparsity assumptions to actually show how to learn these, because this D depends on the length of your state vector. And if it's over parameterized, then I guess D will be very large.
I'd like to end the discussion here. Thank you, Tuhin, for a wonderful talk. We'll proceed to the last talk of this session, which focuses on universal simulation of dynamics using recurrent neural nets. Talk will be given by Joshua Hanson, joint work with Max Raginsky.
Okay. Okay, can everyone see the slides? Good.
Yes. Yes.
Okay. So I'll begin. Thank you for the introduction. I'll begin by talking about some of the motivation for this work. So it's been known for some time that recurrent neural nets can reproduce finite time horizon trajectories for continuous time dynamical systems. So this was proven in a paper by Funahashi called Approximation of Dynamical Systems by CTRNNs. But this type of error bound in the paper, it uses a finite time horizon and requires that it be chosen at training time in construction of the net. So it doesn't allow the time horizon to be chosen by the user at runtime. So if you want to use an RNN in a simulation or long-term forecasting or any applications where the time horizon is unknown a priori and want to bound the error, then we need a different approach to a similar result. So in this work, we look at under what conditions can RNNs simulate systems on an infinite time horizon. And also under certain stability conditions, if we have a quantitative characterization of these stability conditions, how can we take advantage of that to bound the network dimensions to achieve a certain error tolerance? So these the results we're going for are sort of motivated by the goal to establish more rigorous uncertainty quantification methods for neural network-based modeling and machine learning, which is important for scientific applications, where understanding the uncertainty and error is just as important as the quality of the model. So the setting we're considering are dynamical systems of the form x dot equals f of xu with some output map, which depends on the state. And we can assume without loss of generality that the output map is linear. If needed, we can augment the dynamics with derivatives of the output. But so in this case, we just assume that it's linear. We also consider uniformly bounded inputs, so vector valued inputs as a function of time. And in this last point, highlight some of the notation we're using for the flow of the dynamical system, which sort of captures all the information needed to determine a solution uniquely. So the initial condition and at what time it starts the input. We also call the set script X positively invariant if this flow remains in this positively invariant set for all time and for all inputs. So the notion of stability that will give us the result we're looking for is called uniform asymptotic incremental stability. So we say a system has this property on some positively invariant set X for a set of inputs. If we can find a function beta of class KL, which bounds the difference in trajectories due to two different initial conditions. So it's called class KL because the first argument behaves like a nonlinear controller gain, and the second argument behaves like a nonlinear observer gain. So it's continuous in both arguments, strictly increasing in the first, strictly decreasing in the second. And the details are in this last bullet point here on a class KL function. But the purpose of this function is to bound the transient response, to characterize how quickly the system will forget its initial condition. And if it forgets it quickly enough, then we can establish error bounds which hold on an infinite timescale. So an example of this property is exponential stability, and the function beta is given by decaying exponential. But this property is more general and can encompass slower transient responses as well. So the next construction that we want to highlight is this notion of simulation, which is different than taking a dynamical system and approximating it directly with a neural network model, but instead we just want to capture the topological properties of the dynamical system. So if there's a continuous map between the state spaces, that's good enough because we can learn that map and then achieve the approximation via this continuous transformation. So if we have two different dynamical systems, one is like an original system that's unknown and you want to model, and one would be the model. We say that the model system will simulate the original system on sets K and U. So K is the set of initial conditions and U is a set of inputs, up to some accuracy for times in some set. If there are two continuous maps between the original state space and the model state space, which will map the initial condition of the original system into the model state space, and the other map, alpha, will map the trajectory from the model back into the original state space. And if the results are close, then we say that it simulates, the model will simulate the original system. So an easy way to think about this is to draw this out as a commutative or an approximately commutative diagram, where if you follow the paths, then instead of commuting exactly, if they approximately commute, then we say the system sigma tilde approximates the original system. So what you need to find here, if you want to learn some system, is you have to learn sigma tilde and the transformation maps alpha and gamma. But this is a more general notion than just trying to take an RNN where the state of the RNN will model the state of the original system directly, which is more restrictive. So this allows us to get around some technical details of trying to do the former. So the assumptions for our main result are as follows. The first is a relatively standard assumption that the flow of the system that you want to approximate has to stay in some compact set. So we phrase this as if there's a compact set of initial conditions such that for each initial condition in that set K, the trajectory will stay in some other set centered around that initial condition. And then so the trajectory for any of these initial conditions will stay in the union, and this will be compact because the set of initial conditions is compact, and each of the kind of balloon sets around each point is also compact. So that's the first assumption. And the second is that the system is uniformly asymptotically incrementally stable on a positively invariant set for some set of inputs. And then the key assumption, which will give us the result, is that this function beta, which controls the transient decay, is integrable. So with this said, our main result is the following, that if you have a system which satisfies the two previous assumptions, then you can construct a recurrent neural net such that the trajectory of the recurrent neural net approximates the original system to arbitrary accuracy for an infinite time scale. And the mappings alpha and gamma in the simulation are linear, and they'll be constructed in the proof. So instead of going through super technical details, I'm just going to give a quick outline of the proof. The first step is to construct a bump function around the space that the trajectory of the original system lies on. And by approximating this bump function by a feed-forward neural net, we can guarantee, this allows us to guarantee that the flow of the constructed system will stay in some other compact set. And then using this, we can apply a result from von Handel that bounds the difference of flows from two systems based on the error in their two right-hand sides. And because beta is integrable, we can just plug in the approximation error for the feed-forward neural net and the integral of this beta. And this gives us a bound on the error between the flow of the RNN and the original system, which will hold for all time. So this system is an ODE with the right hand described by feed-forward neural nets. So we follow a procedure outlined by Sontag in a paper called Neural Nets as Systems, Models, and Controllers to simulate the feed-forward neural net ODE by a recurrent net. So we essentially take all the weight matrices and collapse them into just one, which is inside the argument of the nonlinearity. And following this process also gives us the linear maps, which transform between the state spaces. So the last slide is to sort of address the goal that I mentioned earlier about uncertainty quantification. So what we contribute in this paper is a way to apply results, quantitative results for feed-forward neural nets, which say of the form, like if you have some error tolerance, how many neurons do you need in a feed-forward neural net to approximate a function to give an error tolerance? So we can adapt these types of results for feed-forward neural nets to recurrent nets, which are designed to approximate dynamical systems. So we take a result from Barron from a long time ago for one hidden layer nets with sigmoidal activation functions that says that the sup norm error is order 1 over root n. And we essentially take this result and adapt it to our construction for recurrent nets to give a quantitative bound on the error, to estimate the number of neurons sufficient to establish a quantitative bound on the error, which will hold for all time. So this is all I have. And hopefully we're under time still. If there are any questions, I can answer those.
So one question is about what are some examples for this incremental stability condition of example of systems?
So as mentioned earlier, exponential stability is one example. Another example is sort of like polynomial on time, but the exponents are negative instead of positive. So like x to the minus or t to the minus alpha, things like this. Basically, any function where the dependence on time decays and is strictly decreasing, so that's all that's necessary for this uniform asymptotic incremental stability. So it's something like exponential stability, but the transients can be as slow as you want. To apply this result, that response has to be integral in time, but the assumption itself is fairly general. The only purpose of beta is just to control the decay rate, and there are lots of types of functions which satisfy the KL class KL assumption.
And another question is the following: is there a reason for using incremental stability but not incremental input to state stability? And if there is an assumption on the class of input signals?
So the only assumption we've used on the class of input signals is that they're uniformly bounded. I'm considering in another work input to state stability, where there's also some control on the size of the input. For this work, we're just trying to control the transient decay of the dependence on the initial condition. So and this isn't really dependent on the input. But in some future work, I'm considering input to state stability as well. We've just chosen this for this work because it gives us the result, and it captures the idea that we wanted to capture, which is controlling the transient response, dependent on the initial condition.
Okay, so Joshua, thank you very much for a wonderful talk, as well as bringing us back on time. So I really appreciate that. This concludes the first session of the second conference for Learning for Dynamics and Control. I'd like to thank all the speakers for a wonderful session. And I'm going to pass it to Alex Bayan, who is going to have a message from our sponsors.
Hi again, Alex Bayan from UC Berkeley. So again, want to reiterate, it's our real pleasure to acknowledge our sponsors today, and the fact that without their generous support to this organization for this conference, it would really not have been possible without their donations. So we're excited to have them also for next year's conference. And so I'm going to reiterate our sponsors are Bosch, Merle, MathWorks, and TRI. We also want to acknowledge the ONR and National Science Foundation for their continuous support. And for next year's L4DC, you'll hopefully be able to meet them in person at the conference, and we'll really look forward to welcoming all of you and the sponsors at the conference. And so this year, as part of our joint association with them, we're very proud to showcase you a short video for each of our sponsors, and we're now going to proceed with MathWorks. And Ben, I will hand it over to you.
Reinforcement Learning Toolbox lets you implement controllers and decision-making algorithms for autonomous systems such as robots and self-driving cars. You can create deep neural network policies and value functions with Deep Network Designer, or programmatically with built-in functions. Define an agent by combining the policy with built-in training algorithms, such as actor-critic methods or DeepQ network. You can create environments in both MATLAB and Simulink. In Simulink, create a model that describes the environment dynamics and reward signal. Use the agent block to interface the environment model with the agent. For MATLAB environments, you may start with provided templates and make modifications as needed. After you complete the training process, you can verify the trained agent with the simulation environment and generate CUDA and C or C++ code to deploy the trained policy. For more information, please check out the product page. MathWorks has various resources for online teaching. MATLAB Tech Talks are educational videos that you can leverage to supplement your teaching of engineering concepts. Feel free to check out our free video collection by visiting the link or scanning the QR code. With MATLAB Live Editor, you can create interactive exercises where descriptive text and executable code are combined in a single document. Using MATLAB Online, students can run these exercises from any web browser without needing to install MATLAB. You can save instruction time by leveraging the free interactive tutorials on MATLAB Simulink machine learning, deep learning, and stateflow. For more information on available resources, please check out our website.
Just a reminder that we'll return at 10:30 Pacific time. That's approximately 10 minutes from now. See you shortly. Okay, it is 10:30 Pacific time. Welcome back. We're now going to move to a session that is going to be focused on everybody's favorite optimal control problem, namely the linear quadratic regulator. We have 3 great talks on this topic, and I'm very excited to see them. The first one is going to be given by Peter Coppens. And Peter, if you could share your screen so we can start to see your slides, that would be great. See if that works. Looks great. Awesome. So Peter is going to tell us a little bit more about distributionally robust LQR. Take it away, Peter.
Yes, thank you very much. So yeah, we'll be presenting on data-driven distributionally robust LQR with multiplicative noise specifically. So let's begin by first giving a bit of a high-level overview of presenting the need for data-driven learning methods and the framework within which we will operate. So a large portion of basic control here is built on employing models, as you've seen today. Controllers are synthesized to behave optimally within this model, but when you have misestimates, then controllers can fail. So in applications like self-driving cars, such failure can lead to potentially dangerous situations. So in the literature, methods like robust control exist that try to deal with a potential mismatch between model and reality. So all too often, such methods, however, encounter a different issue, conservativeness. Your controller will give up on being optimal and will behave very suboptimally, all at the cost of staying safe. So we can take a term from machine learning here, say that we want controllers that generalize. And in the area of control, they should generalize in 2 ways. First of all, safety guarantees like constraint satisfaction and stability should generalize under model errors. And secondly, performance should not be sacrificed too much, and it should generalize as well. So when developing safe controllers, we should always keep these 2 in mind. Doing so should enable us to deal with a large variety of applications where mitigating uncertainty is key. A list of examples are given here, and they can vary from financial applications to autonomous vehicles and aerospace applications. So that gives us a motivation. So now I'll present a framework that allows controllers to learn to generalize in these 2 ways. As I mentioned, most basic approaches focus on this model here. Such a model is often constructed based on some system identification procedure or on first principles. The error accompanying such methods is then sometimes ignored, leading to the issues discussed previously. So the goal of our approach and many other recent approaches is to include this ambiguity throughout the design. And this approach is, for example, called course ID control, as introduced by Ben in the paper below. And so it needs the development of 2 components, basically. So first, it requires knowledge on the exact ambiguity on the model, which we will refer to as the quantification step. And secondly, controllers should be synthesized to be robust against this ambiguity, which we will refer to as the robustify step. And so when all of these components are sufficiently well developed, we can start employing learning. After all, if we can predict the ambiguity and develop controllers that are robust against it, we can also make our controllers less conservative as more data is gathered. And generalization with respect to safety is always guaranteed, and generalization with respect to performance is acquired as more data is gathered. This is what you would expect from a nice control scheme. So it's important to note is that there are multiple options in how we can implement this robustify step. And a good place to look for such options is the field of robust optimization. So the classical option here is to parameterize your uncertainty through some vector, which varies within some set determined through the quantification step. And your controller should then be optimal for the worst case vector in this set, which means that it can only be better in practice, assuming that your set W has been determined correctly. And so from this approach, we can get strong guarantees, but it can be a bit suboptimal since data could infer that certain perturbations are more likely than others. And this is not incorporated in this design. So another approach is then the stochastic approach, where the vector is assumed random. We can then solve a stochastic optimization problem, which is more optimal, but the quantification step is more challenging. After all, you need to know the exact distribution, otherwise you have no real guarantees. And this issue led to the development of distributionally robust approaches, which combine both methods. The vector is random and the distribution lies within some ambiguity set. And if this ambiguity set is selected well, then we can get a couple of nice properties. So first of all, we are safe, of course. Second of all, conservatism can decrease with data as we gather more info about the distribution. And we get effects similar to regularization in machine learning here, as is, for example, studied in this paper cited here on distributionally robust logistic regression. Because of these nice properties, distributionally robust optimization has been applied to control before. And we specifically, as the title suggested, will be studying LQR, multiplicative noise LQR. So here you see kind of the familiar LQR problem, but where the major difference now is where we have these multiplicative noise vectors, right? So we will first be looking at the stochastic case where we have some known mean and known covariance. And luckily, this randomness does not change the structure of the problem much. And I can briefly argue why by looking at the Bellman equation. Here, the major difference is that for LQR, this final term here is quadratic in X and U. And now we have this expected value, but we can see that this quadratic nature is still the case right now. So if you evaluate the expected value, we get this expression here, where the boldface matrices are shorthands. What is important is that this is so still quadratic in X and U, and that it also only depends on the mean and the covariance, as you can see. And this implies that we can still formulate some generalized Riccati equation, that the optimal controller is still linear, and that it still can be found by solving some standard semi-definite program like in standard LQR. And this controller will render the system mean square stable instead of normal stability now, making it a safe controller. And it will also be performance, since, well, for this specific case, for this problem setup, it is the true optimum. So importantly, this optimum only depends on the mean and covariance, since this expected value from before only depends on them. So what we now want to study is the case where this distribution, and so this mean and covariance, are uncertain, moving from the basic framework to kind of the coarse ID version. Right, since only these two moments matter, we only need to quantify the uncertainty associated with these two. We will not go into too much detail here on this quantification step. We use techniques from high-dimensional statistics to derive them, but they take quite a lot of time to introduce. So instead, I will just mention the assumptions we make and the structure of the ambiguity set that we use. So first of all, we will assume that we have access to samples of the distribution of W. The isotropic vector of the random variable W should then be sub-Gaussian, and this has to do with the tails of the distribution not being too large, and is a common assumption within high-dimensional statistics. We will look at the isotropic case due to the specific structure of our ambiguity set and to avoid dependencies on the true distribution. And note that this assumption, however, still works for the case where W is Gaussian and for the case where it has bounded support, so it is quite general. So finally, we will be using the following estimators for the mean and the covariance. So you can see that these are kind of sums of vectors or matrices, random vectors and random matrices, which is quite a common thing to study in high-dimensional statistics. So the structure of our ambiguity set is that the one proposed by de Lagrangier. The idea here is that we create a set of all distributions whose mean and covariance, depicted in red here, are constrained as described on the right. So we have an elliptic constraint on the mean and an LNI constraint on the covariance. So the radii here are then determined such that our ambiguity set contains a true distribution, denoted with a star, with high probability. And this then implies that the guarantees associated with the controller robustified against such an ambiguity hold with the same confidence level. The resulting radii have some nice properties. First of all, they decrease with 1 over the square root of samples, which is a common rate of decrease when dealing with estimators that are sums of random vectors or matrices. Second, our radii do not depend on the true distribution at all, which makes it applicable in practice, something that is not often the case for other high-dimensional statistics results. And third, we need a sufficient amount of samples before the bounds can be derived. And this makes sense since we assume nothing about distribution. The values of our covariance matrix could be 1 or 1 million, we don't know. Now, overall, this ambiguity set can actually be visualized in the 2D case, so where our noise vector has only 2 dimensions. And then we can get the following behavior. So you see that the ambiguity set decreases as we gather more data. Right. So that is very briefly our quantification step. Now for our synthesis step, we will then need to solve the following distributionally robust optimization problem. So this one, where we maximize over distribution. And we will look at 2 cases. The first where only the covariance is unknown, and the second where the mean is unknown as well. For the uncertain covariance case, we only need to maximize over possible covariance matrices. And the reason why we first look at this specific case is because all of our nice properties from before actually still hold. After all, if we look at the Bellman equation associated with this problem, then we can show that this worst case expected value is still quadratic in X and U, since all we do is replace the true covariance with this worst case covariance depicted here. So we still have a generalized Riccati equation that we can solve, and its solution has all of the same properties as before. But now mean square stability holds with high probability. Instead of our controller being the true optimum, it converges to the true optimum as more samples are gathered. So it is consistent. Since it now depends, this is because it now depends on the radius here, and the sample covariance, and this radius converges to 1 as you gather more samples. So for the full uncertainty case then, where we maximize over the full ambiguity set, things are less nice. Since the exact solution to the Bellman equation is no longer quadratic, in fact, its solution is intractable. So we will resort to approximations. The first of which is that we've tried to find the best quadratic approximation to the solution of the Bellman equation by solving this problem. And then the constraint here is still the Bellman equation, but with an inequality. And so this we can approximate this problem with a semi-definite program by using some results from robust optimization. So overall, we need to make 2 approximations, yet we are able to still retain a lot of the properties from before. Controller is still linear, and we can prove that it still renders the system closed loop a mean square stable with high probability. But also our controllers are still consistent. And in the paper, we illustrate this through an experiment, but it's not difficult to verify it theoretically as well. What is depicted here is then the result of that experiment, where the y-axis is the relative difference between the expected infinite horizon cost using our synthesized controllers and the true optimum from our stochastic problem. Right? And you can see that, and the colored area is then a confidence interval around the mean. So what you see nicely is that we have a consistent decrease, which asymptotically follows 1 over the amount of samples. This is something we verified theoretically in a paper recently submitted to CDC. So with that conclusion, we can now move on to some suggestions to future work. We would first want to make our assumptions on the data less restrictive, starting with a condition on the amount of samples, which could be removed by using some prior knowledge about the distribution provided by the designer. We also plan to look at the case where state measurements are gathered. We have estimators already, yet finding an ambiguity set that does not depend on true distribution is more challenging. And we will, of course, want to extend results from distributionally robust control to the constraint case or to the partially observed case, but this is in a more distant future. So that concludes the talk. Thank you for your attention, and I guess I have some time for questions too.
Thank you, Peter. That was great. I'm going to pass the microphone to Jorge Amania, who is going to be moderating the questions during this session.
Hi, Peter. Thank you for the talk. The first question is, in what kind of settings is it reasonable to expect multiplicative noise? Like, how does it occur naturally? And can you comment between the advantages of studying multiplicative noise and compared to the additive noise that is usually used in LQR?
Yeah, so for multiplicative noise, the applications that I mentioned in the beginning, they are actually applications where there are results that study multiplicative noise for this case. Right? So it tends to be when you have a large amount of factors influencing your problem, like in the financial case, for example, that make your noise IID, for example, and you can sometimes then approximate these dynamics through linear dynamics. Now, how this relates to the normal LQR problem, there are some results by Gravel, for example. I think he submitted a paper to this conference as well, who studies how these two are related. So if you have a multiplicative noise system and you have a controller that stabilizes that system, it actually robustly stabilizes a normal linear system as well in some sense. But these connections are not completely examined, but there are some results here.
Great, thank you. And a second question is, how do you obtain samples of W? I think you directly use samples of W in your method. How are these obtained in practice?
Yeah, so this is probably one of the major limitations of the current setup. So you could consider laboratory cases where maybe you would be able to get these distributions, but these samples. This is also why we want to look at the case where we have only state measurements, which I mentioned in my future work, because that would make our method more applicable, right? And so for that case, we have estimators, as I mentioned, but it's a bit more difficult to get bounds that only depend on data that we have knowledge about.
I see. Great. And a clarifying question, do you assume knowledge of the matrices AI? And if these are not known a priori, what can you do?
Yeah, so we do assume knowledge about those at the moment. I guess if you don't have prior knowledge about them, then you would have to resort to some other robust methods stacked on top of this, which would probably make the overall result more robust, more conservative. Yeah, overall, it is possible if you have more uncertain terms in your matrices, you can, of course, introduce these into these multiplicative noise terms. But then again, you need samples from these. So this is also something where these samples from the states would actually help in this extension.
That's excellent. Thank you so much, Peter. It was a great talk. Okay. We're now going to move to our next talk in the session, so which will be given by Michiel. who will share his screen in a moment, I think. That works.
Thank you very much.
Thank you, Peter. Michiel, did your screen sharing work?
Actually, it tells me you cannot start screen share while the other participant is sharing. So I guess Peter has to stop it first.
He stopped it. Now let's try it again.
Okay, so.
Brilliant. Wonderful. So now we're going to hear a talk by Michiel Jovanovic from USC about learning model-free LQR using a random search technique.
Thank you, Ben. Thanks for putting this exciting event together and for bringing friends and colleagues, at least virtually. So as Ben mentioned, I'll be talking about convergence and sample complexity of a random search method for model-free linear quadratic regulator. And this is a joint work with my student Hessam and our friend Mahdi. And the LQR problem is a standard topic in control theory. It goes back to 60s and it involves minimization of a quadratic objective function for linear dynamical systems. So there are many versions of this problem, but the simplest instance is given by linear time invariant systems where state vector evolves according to the state equation here with an infinite horizon. And we consider continuous time problem in which evolution of the state vector is governed by this first order differential equation in the presence of control input u with a random initial condition x naught. So matrices A and B are constant matrices that determine model parameters, and these matrices Q and R are positive definite matrices that specify state and control weights. So I need to emphasize that minimization is done over all state and control trajectories, and the globally optimal solution is given by this linear state feedback policy, which tells you essentially that at every time instant you form control action by acting on the vector of available state measurements with a fixed matrix K. And this matrix K can be obtained from a positive definite solution of the algebraic Riccati equation, and this unique positive definite solution exists under mild system theoretic conditions. So the challenge that arises in modern setup is that you very often don't have access to model parameters. Namely, in order to compute solution of algebraic Riccati equation, you need these matrices A and B, and they may not be available. So the question is then what to do in a situation like this. And one way perhaps to approach this problem is to use data in an attempt to identify model parameters and then to move from there. And Ben and his group have taught us in recent years how this should be done properly. An alternative approach that we are going to take is to attempt to learn feedback policy by optimizing over feedback gain matrices. And you can easily express LQR cost as a function of feedback gain. And this approach received actually lots of attention in the last couple of years. And effort has focused on establishing convergence and statistical properties of gradient-based techniques. And these are challenging questions for two reasons. First of all, it's a standard fact that LQR cost is a non-convex function of the feedback gain matrix. And in the absence of models, you have a burden of establishing statistical properties, namely sample complexity of your optimization-based techniques. And the next slide very briefly summarizes what we've done in this area. We considered the random search method for model-free LQR, and we established linear convergence over the set of stabilizing feedback gains and logarithmic sample complexity with respect to the reciprocal of the desired accuracy. So in the remainder of my talk, what I would like to do is to tell you what we mean by random search method. I'll tell you what we've done and also how our results compare to the state of the art in this rapidly emerging area. And what I would like to highlight is that our results hold with high probability, as you will see in a moment. So very briefly, what allows you to establish linear convergence of gradient descent is smoothness and gradient dominance property of the LQR cost over its sublevel sets. And the way you should think of gradient dominance is really PL type of a condition that relaxes strong convexity and extends this to a broader class of functions, still allowing you to establish linear convergence. And these two properties have been utilized in a recent work by UW group to prove global convergence of gradient descent, global over the set of stabilizing feedback gain, for gains for discrete time systems. And we have provided an alternative proof that utilizes standard system theoretic convex reparametrization for continuous time systems. And this was reported last year at CDC. The challenge is that when you don't have a model, you don't have an access to gradients. Namely, you can only access random function values, perhaps by running experiment or by asking your friends who are domain experts to allow you access to their simulation engine. Perhaps they would give you a luxury of running computational or simulation experiments without telling you what is under the hood. And in this setup, you can provide a current value of the feedback gain and an initial condition in order to obtain a random value of the LQR cost. And then the real LQR cost is obtained by computing expectation over initial conditions, which we assume to be zero mean unit variance with bounded sub-Gaussian norm. And this slide summarizes really what we mean by random search method for model-free LQR. So what random search method attempts to do is to emulate gradient descent by using essentially random function values in order to estimate the gradient. And we are not using random search, uninformed search direction. We are tapping into the area of derivative-free or zero-order optimization, and a couple of alternative approaches of how you can compute gradient estimate using a single sample are given here. This first expression is so-called two-point gradient estimate, which may remind you of a central difference scheme from numerical analysis. What differentiates two-point scheme from one-point scheme is that you have ability to compute a random value of the cost function for two different values of the feedback gain, but with the same initial condition. And obviously this may be challenging in experiments, but if you have an access to simulation engine, you can perhaps do it. In contrast to that, in one point estimate, you can evaluate objective function at one particular gain for one initial condition. There is significant difference between them. It's the standard fact that two-point gradient schemes reduce variance. What I would like to highlight is that you need to be a little bit careful here in how you choose these random matrices U, which are assumed to be uniformly distributed over sphere, and this smoothing parameter R, because you need to guarantee closed loop stability, and all of these issues are addressed in our paper. Of course, in applications, you are not bound to using a single sample. You can use multiple samples by perhaps utilizing mini-batch gradient estimate. This would require running multiple simulations, and then the relevant question becomes how many samples and how many iterations you need in order for your random search method to emulate properties of gradient descent. And this slide summarizes the main contribution of our work. What HESA managed to show is that if you use random search method for model-free LQR, you can achieve desired accuracy epsilon with high probability under the following upper bound for total number of iterations. So T has to be logarithmic function of the reciprocal of the desired accuracy, and the number of samples per iteration that you need to utilize is proportional to the state dimension. So N here denotes the number of components in your state vector. For example, for standard mass spring system, N would be 2. So there is also this logarithmic dependence, but that's inconsequential. I'd like to highlight that in contrast to other results in the literature, this bound on N does not depend on epsilon. C is a constant that depends on problem parameters, but it is not a function of the desired accuracy. And sample complexity is given by a product between T and N. And obviously, the result that we establish here is that sample complexity is proportional, linearly scales with the problem dimension, with the number of states, and logarithmically with 1 over epsilon. So, and all details are contained in our archive preprint. Conference publication only summarizes high-level points. So I don't have, unfortunately, too much time to tell you how this compares to state-of-the-art in this literature, but let me just very briefly highlight the impressive paper by UC Berkeley group, where they compared 1 and 2 point gradient estimates. They managed to establish polynomial sample complexity, sublinear convergence rate with decreasing step size. This is really an impressive work that opened our eyes at many different levels and inspired us actually to closely examine 2 point gradient estimate. And then what they also managed to show, and this builds on the work of University of Washington group, that if instead of using single sample, you utilize mini batch gradient estimate with 1 point scheme, you can have polynomial complexity in terms of 1 over epsilon with a linear rate of convergence and a fixed step size. So one way to establish these results is to try to control the gradient estimation error. And this is not what we do in our approach. In our approach, key feature of our proof is really that we don't try to control gradient estimation error. Rather, we exploit the problem structure and utilize tools from non-asymptotic statistics to show that gradient estimate concentrates with high probability when projected to the direction of the gradient. And all of our results hold for 2 point estimates. So the way we managed to show this is that rather than using gradient descent, we utilize actually approximate gradient descent. Namely, it's a standard fact in optimization that you can achieve linear convergence with fixed step size as long as your direction has large enough projection in the direction of the true gradient, and as long as its norm is not too big relative to the norm of the true gradient. Obviously, this holds in deterministic setup, and in our work, we showed that these two events hold with high probability. So again, all details are contained in the paper, but let me just give you an indication of what our results demonstrate from applied point of view. Here I consider mass spring a bunch of cards that are connected by springs and dampers with inverted pendulum on the top of them. Each card has a force control. And the objective here is to design LQR in an offline fashion, I have to emphasize. So everything here is done in an offline fashion using around certain operating point. And what these two plots here show is essentially histograms of these two events that we want to hold with high probability. And this is obviously, with the probability of 0.994 and probability 995. If you choose these parameters, theta 1 and theta 2 properly, you have this. So, and we have linear convergence with a smooth curve. There are no stochastic oscillations that are typical for stochastic algorithms. So what I would like to highlight is that there are many open challenges in this area. One of them arises in the area of structured feedback synthesis, where perhaps you would like to utilize limited information exchange between your different subsystems, and you want to promote sparsity in the feedback gain. This is a non-smooth problem, and it's an open question of how many of these things that we establish here extend to this setup. And obviously, dynamic feedback synthesis is a big open challenge for reinforcement learning. The most important slide, all credit goes to Hessam and Magdi. They are fantastic. They've done all heavy lifting. I'm here just to approve their message, and credit also goes to Fred and Kishan for supporting this work.
Thanks, Michiel. Jorge, you want to take over?
Yes. In a model free setting such as this one, how do you check for controllability?
I mean, we assume that the problem is controllable. I mean, that's a starting point here. And again, I mean, controllability is an integral part of a control design. So, control engineers should be involved from the outset into the mix. Now, how we haven't paid attention to this, but obviously, this would be a challenge in any setup where you are absolutely clueless about the model, right? So the fact that we assume that there is simulation engine already tells you that some domain experts have been on board. So perhaps in collaboration with them, you see what's going on. But in general, this is a challenge in a data-driven setup.
Great, thank you. And how does the condition number enter into your complexity bound? And what is the right notion of condition number?
All details are provided in the paper. Let's not go into these technicalities. Let's talk about big picture.
Unfortunately, we're out of time, so we don't really have.
Okay, all good.
We talked big picture. That was a great talk. Thank you very much.
Thank you. Thanks a lot.
To the open review discussion, where you continue to chat there. I see that there's a lot of free flowing conversation in the chat, which is actually really fun. This has been really quite a fun and energetic event. So for our last talk of this session, we have Jack Umenberger, who is going to tell us about optimistic LQR. Let's see if, and we got, the slides are going. Looking good.
Sorry.
Jack, and you're ready to go, man.
Great. Thank you very much, Ben. And thank you indeed for all the organizers for taking the time to make sure this goes ahead virtually. So this is joint work with my friend and colleague, Thomas. So as I'm sure we're all aware, reinforcement learning has had some pretty spectacular and high-profile success stories in recent years. However, one might make two, not necessarily criticisms, but observations. The first being that typically in RL, there's no requirement that you avoid failure or even bad outcomes during the learning or the exploration phase. And this is typically fine in simulation or in video games, but in real life, we might not like to have our robot crash and have to reset that. Furthermore, exploration often, but not always, is based on trial and error, which can lead to high sample complexity. So in this work, we would like to do exploration that is both robust, and by robust, I mean that we avoid system failure during the exploration phase, and also targeted, meaning that the exploratory actions that we take should provide information that's specifically relevant to the task we're trying to accomplish. And I should also just add, of course, that we're not the only authors to study these considerations, and there's a literature review in the paper. So fortunately, Ben has tempered our expectations, and I will indeed be talking about linear quadratic control. So here we have a linear time invariant system. X here is our state that we assume is fully observable without any measurement noise. U is the input that we can control, and W is this disturbance that we don't get to observe, but we assume that it's normally distributed. Our task is to minimize this quadratic cost function where Q and R are given to us by the user. And we'll be considering state feedback policies that are dynamic in general. So as we've said, if A and B were known, then this would be LQR, which is extremely well understood. But the challenge in our setting is that A and B are unknown, and we have to solve this control problem with only measurements of X and U. So in the absence of the true model parameters, we can build a model from data, and this model has two key elements. The first are these nominal parameter estimates, A hat and B hat. These represent, in some sense, our best guess of the true model parameters. And we also have this set theta, which is assumed to contain the true model, at least with some, or the true system rather, at least with some high probability. So one strategy to solve the problem would be the so-called certainty equivalence approach. So this just assumes that the true system will behave exactly like the nominal system, and you design the optimal controller for A hat and B hat. And indeed, recent work by Ahmadi and others has shown that this actually achieves almost the optimal regret. So it's certainly quite a sensible strategy to take. However, this relies on the assumption that the uncertainty is sufficiently small. So in particular, if this set theta is quite large, then it's possible that the certainty equivalent controller may not stabilize the true system, and this closed loop instability could lead to quite poor performance in practice. As such, it might be desirable to impose a model stability constraint. And here we see our goal is still to minimize the cost function for the nominal parameters, just like in certainty equivalent control. But we'd also like to insist that the controller K robustly stabilizes every model in this set. Because we're considering the nominal or most likely model parameters, we call this an optimistic strategy, as opposed to if we had the worst case model parameters in this set. And also because we robustly stabilize the system, this is where our robust exploration comes in. So we can think of this, the problem we're trying to solve as wanting to minimize this cost for the nominal parameters, just like in certainty equivalent control to get the low regret. But we have this robust stability constraint, which prevents us from doing so. And the robust stability constraint gives us some guarantees on stability, but it might come at the expense of some conservatism. So at least in the context of this problem, we can think of the role of exploration as gathering data so that we can reduce the size of this set of uncertain models data in such a way that this robustness constraint is as least restrictive as possible. So you can see the uncertainty set being shrunk down here after exploration. So to be a bit more precise, we need to quantify the size of the uncertainty set in some sense. And one possibility is to measure it in an absolute sense, for example, via the 2 norm. So that's the error between the 2 norm of the error between the actual true parameters and our best guess of the parameters. And you can think of this, this measurement of error as a ball that goes around the uncertainty set of radius epsilon. This is quite common and certainly a reasonable thing to do. And in this setting, exploration would involve trying to reduce the size of this radius epsilon to get a smaller set, such that when you solve the control problem after exploration, I'm just wondering if this is blocking the screen, but sorry if that was blocking it, but after the exploration, this robust constraint is less conservative. And this is a reasonable, this is a reasonable thing to try, but there's no structure in this representation of uncertainty. It's just a scale. So, however, it's also possible to use a representation that retains more structure. So, for instance, we could consider this matrix D such that this matrix inequality holds, where X is the same parameter error that we considered for the 2 norm. And then our goal in exploration is to reduce this matrix D in some sense. But as you can see, now this notion of reducing uncertainty becomes a little bit more nuanced. We just don't have a scalar to shrink. We have to rather reshape this set of models by changing the spectral properties of D so that we can minimize the cost of this control problem when we use this new shrunk uncertainty set. So hopefully my Zoom is not blocking my final bullet point here, but you can see that it might be the case that this control problem is more sensitive to uncertainty in some directions of the parameter space than others. So for example, it might be that uncertainty in this direction is quite important to reduce. And so even though we have a larger overall uncertainty compared to this set here, this will actually give us a lower cost. And this is what we mean by targeted exploration, that we're in some sense targeting the parameters or targeting reduction of uncertainty in the parameters that matter most for control. So this is just a cartoon picture of what we hope might happen, but we have some evidence to suggest that this can in fact occur in practice. So I won't go through the details for time constraints, but due to time constraints. But here we can see that this strategy that is, maybe Ben, could you jump in and just tell me if my Zoom is blocking my slides or not?
It looks fine.
Okay, that's good. It's blocking my ability to point, but good. So for this strategy that targets structured uncertainty reduction, it achieves lower cost. But you'll notice that actually the 2 norm of that uncertainty set is higher than for the epsilon, than for the one that targets epsilon. So that's kind of this picture here. Okay, so again, due to time constraints, I don't have time to go through all the technical details. I'm happy to answer questions, but let me just quickly say that To formulate this set of uncertain models theta, we can leverage our Gaussian assumptions. Turns out to be quite straightforward. And to actually synthesize the robust controllers, we make use of system-level synthesis, and in particular, a result that allows us to formulate the robustness condition as a linear matrix inequality that is linear in this matrix D. Remember, D is what's capturing the uncertainty here. Okay, so let me close with a quick example of how to apply this. So we have our time horizon over which we would like to control the system, and we'll partition it into two intervals, one which is for the purpose of exploration, and the other which is for the purpose of exploitation. In general, we could partition this into as many intervals as we like, but I'll just use two for simplicity of the illustration. And so our problem is at the beginning to design a dual controller that we will deploy at time 0 based on some prior knowledge or initial data. And that will be deployed during this exploration phase. It will incur some cost here. After that phase, we can collect the data that we just observed, build a new model here in blue, and use that new model to design and then deploy a new robust controller that will operate in the exploitation regime. And so our task is to minimize the total cost of both exploration and exploitation. Okay, so here we have a numerical illustration in which we compare three methods. The first I'm calling nominal robust control. So here the goal is just to minimize the cost for the nominal model subject to the robust stability constraint. There's no explicit exploration baked into the method at all. The second is dual control, which is what I've been discussing so far. And the third is so what I'm calling a greedy approach. And this involves taking the best robustly stabilizing controller that you can find, so it minimizes the cost as much as possible, but then adding this exploration signal, which is distributed normally. And our goal, and what we'll do is we'll maximize the variance so that we add as much exploration as possible, subject to the constraint that the dual method and the greedy method both have the same exploration cost. So that's what you can see down here. Just as a reminder, this is the problem that we're considering, an explore phase and an exploit phase. And so you can see here that by design, both the greedy and the dual control have the same exploration cost. But in the, you can also notice, I should point out that the costs are normalized relative to the nominal robust control. So a cost of 1 means it has the same control, the same cost rather. However, during the exploitation phase, I should say, because we've been able to reduce the uncertainty, our cost is lower. However, the reduction in uncertainty and reduction in cost is quite low for the greedy strategy, even though it had the same exploration budget, which means that if you look at the total cost of the strategy, which simply adds up the exploration and exploitation costs, it actually does worse than this strategy that's trying to explore actually does worse than just the kind of certainty equivalent thing. However, the robust dual control can do better. So let me wrap up there. I'm not sure how I'm going for time, but maybe I'll leave these kind of key points on the slide and be happy to take some questions.
Thanks, Jack. That's right on time.
Cool.
I'll pass the mic back to Horia.
Thank you, Jack, for the talk. Do you think it's possible to quantify analytically the data requirements of your method? Or have you done so already?
What do you mean by the data requirements? Like the Gaussian assumption of the noise, or?
Like precisely quantifying how much data you need for your method to achieve a certain suboptimality gap with respect to the optimal controller?
Yeah, that's a good question. I mean, a priori, without knowing the true model, it's maybe hard to know the what the true optimal performance is. So if you could solve for the best case model in the set of uncertain models, that might give you some kind of lower bound. And then you can certainly kind of reverse the process and back out what, because the robust constraint is linear in that matrix D, you could in some sense back out what kind of D you need to achieve a certain cost. And that might allow you to analyze that.
Okay, thank you. Are there connections between the matrix D and dual control, which encodes uncertainty structure and multiplicative noise control?
What's meant by dual control? Sorry.
Yeah, I'm actually not entirely sure. I'm sorry.
I mean, I can I can say that I didn't have time to go into it, but this matrix D is essentially the empirical covariance matrix for the data that you observe. So it has the rather nice property that in the LQR problem, it shows up in two places. The first place it shows up in is the cost. So of course, it's a quadratic cost. So you can represent it as essentially an inner product between your weight matrices and D. But it also shows up, as I talked about briefly, in your uncertainty quantification. As characterizing the size of that elliptical uncertainty set. And so it's very nice. In this formulation, it captures the exploration exploration trade-off very nicely in that you want to minimize D in some sense to lower the cost, but you want to maximize D in some sense to make that uncertainty as small as possible. So in this convex formulation, you can actually trade off for that optimal D optimally because it's a closed form. It's a convex program. So I'm not sure if that answers the question in any way, but yeah. Okay.
Let's take one more.
Okay. How do you know that the closed loop system remains robustly stable even though K is constantly changing as we learn more information during exploration?
Yep, that's a great question. So we have these epochs, we have this exploration phase and this exploitation phase. And whenever we design a controller, we enforce robust stability. So I didn't go into the details here, but you only update the controller at the end of the epoch. So there's no changing of the gains during that exploration or exploitation phase, only at the end. So we just always enforce robust stability. It's a good question.
All right, thanks again, Jack. Thanks again to all of our speakers in this session. That was really fun. I would like to pass the mic back to Alex Byan.
Yeah, hi. So it's as we're going into the break, again, our pleasure to acknowledge our sponsors today who have generously supported this conference. Without them, it would not have been possible. And we also want to acknowledge all of them, Bosch, Merrill, MathWorks, and TRI, as well as the ONR and the National Science Foundation for their support. If you come to the conference next year, or when you come to the conference next year, hopefully you'll be able to meet them in person at the conference, and we look forward to welcoming all of you at the conference. And this year, as part of our joint association with them, we're really proud and happy to showcase to you a short video for each of them. And now we're going to go with TRI. And Ben, I will hand it over to you.
Hi everyone, and welcome to this year's L4DC conference. My name is Dr. Carrie Bobir-Chiu, and I manage the control team of the driving organization at Toyota Research Institute. Two of the mandates of Toyota Research Institute are to improve vehicle safety and increase vehicle access. My team uses our backgrounds in control theory and dynamics to address these mandates through the implementation of two paradigms for driving. Toyota Chauffeur is a vehicle concept for full autonomy, where the human is removed from control to increase vehicle access by those who cannot normally drive themselves. Toyota Guardian works alongside the driver in parallel autonomy, amplifying the human capabilities for enhanced accident prevention by communicating with the driver and augmenting their commands under emergent circumstances. Alongside the rest of the control community, we are also learning to incorporate our vast amounts of data to inform our control approaches. From problem space definition to model enhancement, from parameter estimation to algorithm design, data gives us insight into the corner cases and elusive limits of model-based design. If you can envision a database of every road vehicle crash, we are envisioning a day when the Guardian and Chauffeur systems can actualize the solution for all of them. Toyota Research Institute is proud to sponsor this year's L4DC conference. I would like to thank you as contributors for advancing the field of control in this data-driven age. Thank you.
All right. We're going to have one more talk today by Catherine Wolfram from UC Berkeley. Catherine's talk will be at 11:30 and is going to discuss the dynamics of energy markets and their impact on society. Should be very interesting, so I hope to see you back in about 10 minutes at 11:30.
I could see your slides fine, Catherine.
Okay. Here they are.
Okay, I'm gonna introduce you, Catherine.
Sounds great. Thank you.
Okay, everybody, it's my pleasure to introduce our final speaker of today's session, and also to introduce Andrea Baichi, who will be helping to moderate this session by collecting up the questions on YouTube and answering and asking some of those to Catherine at the end of her talk. Okay, so it's my pleasure to welcome Catherine Wolfram. Catherine is the Cora Jane Flood Professor of Business Administration at the Haas School of Business at Berkeley. She is also the Associate Dean for Academic Affairs and the Chair of the Faculty at the Haas School of Business. She's the Program Director for the National Bureau of Economic Research's Environment and Energy Resources Program, and she holds affiliate positions in Agriculture and Resource Economics, the Energy and Resources Group at UC Berkeley. Prior to coming to Berkeley, she was a professor of economics at Harvard. Catherine is an expert in the economics of energy markets. She has analyzed rural electrification programs in the developing world, energy efficient programs in the United States, the effects of environment regulations on energy markets, and the impacts of privatization and restructuring in energy systems and energy economics. And she's currently holding and has held randomized control trials for these analyses in the US, in Ghana, and in Kenya. So it's a great pleasure to welcome Catherine.
Great, thanks so much, Claire. And thanks all of you for joining virtually. So just to summarize Claire's introduction, I'm an economist, and this is joint work with a multidisciplinary team that includes engineers. One of those engineers is part of the panel, Noah Klugman, who's working on the sensors. What I thought I would do is start by talking about some of my work on energy access in Africa, because I think this work really motivates why we're interested in using sensors to measure electricity reliability. So we're thinking about blackouts here. But first, at a very high level, I wanted to explain why I'm personally interested in thinking about energy in the developing world. So this is a chart that shows total energy use. So we're adding together gasoline use, natural gas, electricity, converting them all to BTUs, and then plotting usage by non-OECD countries, so roughly emerging markets, and OECD countries. So the solid lines are the actual uses, and then the dotted lines are the Energy Information Administration's projections of future use, but these match projections by other institutions. And so what this suggests is that, first of all, in terms of actual use, the emerging markets have already surpassed the OECD countries in terms of total energy use, certainly not per capita, but in terms of total energy use. And that the vast majority of the future growth that's projected in energy consumption is going to come from these emerging markets. And so by 2050, 2/3 of the energy consumption is going to be in non-OECD countries. So when I looked at this, it struck me that the share of at least economics papers that are written about the energy industry is way out of proportion. So there's probably like 99-to-1 papers written about OECD energy markets compared to non-OECD. But if we want to understand any global energy problem, including climate change, we really need to understand what's happening with the non-OECD countries. So at a very high level, that's what's motivating my interest in these topics. And from a climate change perspective, this kind of rapidly increasing line of energy and energy use in the emerging markets looks frightening, because a lot of this energy will be fossil fuel, or has been fossil fuel historically. But I also wanted to note that there is kind of a flip side to the frightening message from that increasing line, which is the economic development. So here's a graph that's charting for every country. So each dot on this graph is a country, plotted in terms of their GDP per capita log on the log scale and their electricity consumption per capita. And I will say that there are not many relationships in economics that are like this clear and this clearly positive. And so it's very clear that there's a strong positive correlation between GDP per capita as a measure of economic development and electricity consumption per capita. What we don't know, though, is how the causality runs, whether it's the case that as countries get richer, people can afford things like air conditioners and they consume more electricity. So whether the causality goes from GDP per capita to electricity, or whether the opposite is true, that electricity consumption really drives economic development. So at a really fundamental level, I'm interested in understanding this relationship. Is it the causality running from electricity to development or reverse, or some combination of the two? Also, we don't know, we're just summarizing total electricity consumption in the country on a per capita basis, not breaking it down by industrial versus residential, or thinking about the reliability of that electricity. So I think it's important to kind of dive into this and understand this relationship at a deeper level. So with that in mind, whenever you go to a conference on electricity in the developing world, energy in the developing world, very quickly it turns to a discussion of the roughly 1 billion people who live without electricity in their home. The Sustainable Development Goals, for instance, sustainable goal number 7 is to have near universal access of safe and reliable electricity for all people. And so there's a real emphasis on these billion people who live without electricity in their home. And so some colleagues of mine and I wanted to understand, well, like, what is the impact of electrifying, of bringing electricity to the billion people who don't have it? Policymakers often tell stories about how, you bring electricity to people, then kids can study more at night, people can refrigerate food, people can refrigerate medicine. So we really wanted to understand what exactly is going on when you bring people electricity. In order to do that, we've run a randomized control trial on electrification in Western Kenya. So I wanted, with one slide, just to quickly describe what's going on with this randomized control trial. So we started by identifying 150 what we call transformer communities. So think about this as a village kind of defined relative to a transformer. And the transformers were placed as part of a rural electrification initiative designed to electrify schools and marketplaces. So we identified 150 transformers, and then the households that lived within 600 meters of those villages. Then we randomly, just literally coin flip, divided them into treatment and control. And so in the control group, the households were allowed to connect to the electricity grid if they were willing to pay the $400 required to get that connection. In the treatment group, we offered 3 different levels of subsidies for that connection. For one group of 25 villages, we provided them with a free connection. We paid the full $400 cost for the connection. For another group, we gave them about a 70% subsidy, and for a third group, we gave them about a 25% subsidy. And then basically, we let the homes, let the villagers live their lives, and went back. We went back first after 18 months, again after about 32 months, and just recently after 5 years. And we've surveyed these households. And so comparing the treated households to the control households, the treated households, especially in the Black group where we gave them a free electricity connection, there were many more people connected than in the control group. And so we can compare outcomes, see, are kids in the households where they have electricity, are those kids studying more? Are people consuming different types of foods, or how have their lives changed? And so this is the idea of the randomized control trial. And just to emphasize that this initial randomization ensures that on all other economic, social factors that these two groups are identical, that they have the same level of kind of baseline incomes, same average agricultural plot size, lots of things are statistically identical between these two groups. And so we can be confident that the only differences in outcomes after our intervention is due to the fact that people in the treatment group were offered electricity access. And in the case of the free group, they 98% of them took the free electricity access. Okay, so just to describe how this was implemented, we were working together with Innovations for Poverty Action, a local NGO. They held community meetings, tried to describe or to describe the subsidies to the households, especially for the ones where we weren't giving them a full 100% subsidy. There were some steps involved because the households had to deposit money in a bank account. Next, the Rural Electrification Authority showed up and connected the households. You know, we installed on average, I think, 2 poles per our connected households. Here they're putting the drop line to the house. And then finally, Kenya Power showed up to install the prepaid meters, and the households were connected. In order to ensure that they were able to use the electricity, we also gave households, as part of our experiment, these ready boards, which included a light socket and 2 electrical outlets. So that was part of the connection. Okay, so what did we find? We looked at 8 separate outcomes, which we identified as our primary outcomes that we were interested in. And these range from kind of economic things, whether the household was employed in the formal labor sector outside of subsistence agriculture, the number of hours that they worked in the formal labor sector, consumption, asset values. Then we looked at things like health symptoms. If they're using electricity as a replacement for kerosene, maybe they have fewer respiratory issues. We looked at this index of political and social awareness. We asked them just on a scale of 1 to 10, how happy are you? How satisfied are you with your life? And then we also gave the children, roughly kind of 5th grade to 8th grade age children, we gave them math and English tests and to assess whether, if the kids have access to electricity, if they're studying more, are they scoring higher on tests? And in what I have found to be a personally very demoralizing, but intellectually fascinating level, we found nothing. We found a bunch of 0 differences, statistically indistinguishable small differences between the treatment and the control group. So, you know, the Rural Electrification Authority paid on average $1,000, even though it cost the households only $400. It cost the Rural Electrification Authority about $1,000 to connect these households to the grid. And even after 5 years, we're seeing basically no impacts on the households, no measurable impacts. The ones kind of small but statistically significant impact that we did see was on life satisfaction. So people reported being happier. And we can talk about that in the question and answer if you want, but on all these kind of economic terms, in terms of student test scores, people were no different in the treatment group where they had electricity for 5 years compared to the control group. Okay, so one thing that I suspect might be going on is that if you identify the 1 billion people in the world who live without electricity in the home, you've identified the 1 billion poorest people in the world. And so this is a picture of a woman proudly showing her new kind of prepay meter on her mud wall. And so the households that we were bringing electricity to, not only did they lack electricity, they lacked brick or substantial housing material. Some of them lacked anything other than a thatch roof. They lacked flooring. They lacked access to healthcare for their kids. They lacked access to good education. And so it's not clear to me that electricity is number 1 or even number 7 on the list of things that in the immediate future these households need for improved development. I fear that measuring access to healthcare, for instance, or measuring access to education is really messy. It's hard to say, well, how, what does access mean? What does good education mean? Whereas electricity is this nice kind of binary measure. Do you have electricity in the home or not? And so we've fixated on this as an indicator of whether people are poor, and conflated this as an indicator with thinking that it's a determinant of poverty, that alleviating this lack of electricity in their house is something that will change their state of their poverty. And so our results are suggesting that that's not the case, that bringing people electricity when they lack lots of other things does not change their lives. So why am I going through this? Why do I think this is related to reliability? I fear that we are too focused on rural electrification, that there's a lot of money that's being invested in connecting households to the grid. And you might say, well, that's fine. Maybe after 5 years, there's no impact, but maybe after 10 years, you'll see a measurable impact. There's an argument that access to electricity is a right that people have. But I think the point is that this is not a right that is costless, that connecting people to the electricity grid costs a lot of money. And in a lot of cases, they're not using very much electricity. We saw in our experiment that the households who were connected were using on average 3 kilowatt hours per month. The average US household uses 3 kilowatt hours in about 3 hours. And so this is just a not very large amount of electricity. People were not buying appliances. And so they're not, as a result, contributing to the revenue stream of the utilities. And so if the utilities are being asked to connect a lot of households, spend a lot of money on those households, it is potentially at the expense of reliability. And so this is a picture, oops, where's my cursor here? This is a picture of a transformer tower that it's hard to see it from the picture. I tried to line it up with the window panes here, but it's leaning at a very, precarious angle, and just seems like it's about to topple over. And so I fear that by spending a lot of money on rural electrification, we're diverting resources from improving the reliability on the existing grid. And if that's the case, we may be lowering the reliability for schools, like the one where this transformer might be about to topple over. We may be lowering reliability for businesses. And it's possible that by spending money on rural electrification to connect households who aren't using it, who aren't gaining from it, at least in the 5 years, we're diverting the resources away from things like schools and businesses and hospitals, where having less reliable electricity is really a detriment to growth. And so in order to answer that, we need to try to understand the relationship between reliability and firm successes and hospital outcomes, things like that. Okay, so just to kind of put a finer point on the revenue impact that I've been mentioning, this is a graph, focus first on the one on the left, that shows the number of residential, commercial, and industrial meters in Kenya Power. So this is 2001 to 2016. You see some growth in the industrial meters, modest growth in the commercial meters. But what I really want to emphasize is that the number of residential meters has taken off dramatically and is now close to 5 million, or in 2016, close to 5 million. And so what this is showing is that Kenya Power has very actively pursued rural electrification and connected a bunch of new people to the grid. But what this graph on the right is showing you is what's happened to monthly consumption of their residential, commercial, and industrial customers. So commercial and industrial, they're basically flat. Consumption has gone up a bit for their commercial customers, but average residential consumption for residential customers has absolutely fallen off a cliff. And so this is suggesting that our findings in the experiment are consistent with what's happening more broadly nationwide, that as they're connecting more people, they're connecting people who are using fewer and fewer kilowatt hours, and therefore contributing less and less to the utilities bottom line. And therefore the utilities kind of coffers and ability to provide reliability are potentially seriously depleted. Okay, so in order to kind of dive deeper into this question, what happens as reliability goes down, we need to understand more about the relationship between reliability and socioeconomic outcomes. So again, anecdotally, you hear stories about how with poor reliability, companies are forced to spend money on backup generators, and those backup generators, the money that they're spending on the backup generators can effectively work as a tax. I've talked to a company operating in Nigeria, and they said, not only do I have to buy a backup generator, but my accountant has to buy a backup generator. My internet service provider has to buy a backup generator. So, effectively it taxes these companies. So that's where, that's where we really want to try to understand the relationship between reliability and economic growth. In order to do that, though, we need more data on reliability. And so what this map is showing is the one measure of reliability. This is basically like the sum of all customer interruptions, the sum of all outages that customers have experienced, normalized by the number of customers that are served. And so here, kind of darker pink means that customers are experiencing a lot of disruptions. So you're seeing that in like Pakistan and Afghanistan, it looks like they have a lot of disruptions. What you're seeing, though, is that in most of Africa, there's no data. These are the grays. Even in the places where there is data, I think there's some reason, and people who I've talked to who know the local context kind of are suspicious of the data. So it suggests that, for instance, the DRC has similar levels of reliability or similar levels of this measure of reliability to the US. So I think there's just a severe lack of data, a lack of good data on reliability. Without that, from my perspective, the researchers can't measure the benefits of improved reliability. Donors like the World Bank, like the DFID in the UK, can't measure the returns to their investments. And perhaps most importantly, the utilities can't think about how to address poor reliability. They can't, if they can't see the problem, they can't decide how to best address it. So here's where the sensors come in. Working together with the engineers, they have developed this kind of 3-part approach to measuring reliability. And the basic, if you have questions, I'll refer them to Noah during the discussion, but the basic idea is to use the cellular network as a way to send information to a central cloud computing infrastructure about the presence or absence of power. So just very quickly to explain in a kind of simple stylized format how this works. Imagine that you have generation here, some sort of like hydro or fossil fuel plant. Here's the high voltage network, distributing it through the medium voltage network to substations. Here are the low voltage transformers, and then ultimately the customers, households, businesses, etc. So the idea is that the grid watch devices, either the phones that are collecting information or the power watch sensors that Noah and his team have developed, are at the customer level and are really measuring the customer experience with reliability. And what happens is that, so for instance, if there's a high voltage outage or some kind of load shedding because of insufficient generation, then all the grid watch sensors at once, within the same millisecond, will detect the loss of power. Whereas if there's a medium voltage outage, then only sensors kind of connected on the same feeder will experience these simultaneous outages, whereas this one on a different feeder won't experience that outage. And similarly for a low voltage outage, the devices connected to the same transformer will experience the outage, whereas devices connected to an adjacent transformer won't experience the outage. And there's definitely some sophistication going on here, where if a single device experiences an outage, then you think maybe the customer accidentally unplugged the sensor, maybe the customer didn't pay the prepay meter ran out of credits, and so it's not a system-wide outage, it's just a local for that customer outage. And so we've been deploying about 2 or 3 sensors per transformer so that we can identify a system level outage, or at least a transformer level outage separately from a individual customer outage. So most of the utilities that we've talked to in Africa, the one that we're working with most closely is in Ghana, the electricity company of Ghana, also in Kenya. Most of them have SCADA coverage. And so they're monitoring what's going on at the high voltage and the medium voltage level. What GridWatch adds are many things, but they add the ability to see these low voltage outages, to see the outages that the SCADA systems aren't picking up. And I'll show you in a second what we're finding in a pilot deployment in Ghana. I guess I would also add that an advantage of GridWatch is that it's available independent of the utility. So it's something that's monitoring the utility system plugged in at the customer level. It's not, we're not reliant on the relationship with the utility to get it to monitor their system. And so the flow of data, the control of that flow of data is out of the hands of the utility. Okay, so NOAA team are manufacturing these devices. They've founded a company to scale up the manufacturing of the devices. We're using a local team, local project manager overseeing a local team to deploy the devices, to check on them, make sure that they're working right, to resolve any issues that come up if they stop working. So let me just in closing give you kind of some early results from one excuse me, electricity district in Accra, Ghana. So this is a measure of I showed you in the map before what's called SAIDI, which measures the excuse me, the duration of the outages. This is the frequency of the outages, so just the number of outages that people are experiencing. So you can see, and this is what was measured by the electricity company of Ghana in gray. And so you can see that in July, the average customer experienced more than 2.5 outages on average, and slightly more in September. You can also decompose those into what the electricity company of Ghana reported as high voltage outages, what they reported as medium voltage outages, and then you can barely see it. These are what they were reporting as low voltage, excuse me, transformer level outages. Yep. Okay, so it looks like the vast majority of the outages are on the high voltage electricity system. So now let me show you what we were seeing with the GridWatch devices. In terms of large outages that are affecting, I think it was more than 10 devices simultaneously, we're pretty much matching what the utility is seeing from its SCADA system, which is heartening. It means that we seem to be measuring about the same number of outages, if anything, a couple more than what the utility is measuring. But what we find is really interesting is that in addition to this, we're seeing way more small outages, about double in July, slightly less than double in August and September of small outages, of kind of transformer level distribution outages. And so I think there are some really interesting things to understand about why this might be going on, what incentives exist in the utility to report outages, and why they don't seem to be getting the reports on these small outages. But to make the earlier point, to just emphasize the earlier point, if the utility is not seeing these data, how can they address this problem? Whereas the customers are definitely experiencing the problem. Okay, so this is all kind of preparatory work, collecting this very fine-grained, accurate measure of reliability is something that we are going to use and try to measure the socioeconomic impacts of reliability. This is definitely work in progress. Hopefully in another year or two, I'll be able to come back and give you some indications of what the implications are of the poor reliability. But I think that it's going to help us kind of understand this complicated relationship between economic growth and electricity consumption per capita. So just in closing, I want to thank the GridWatch team. It's a active multidisciplinary team with a lot of grad students here in the US, with a project manager in Ghana, and happy to answer questions. I will definitely defer the questions on the sensors to Noah, who's also online.
Thank you very much, Catherine, for that wonderful talk where you emphasized the need to understand reliability versus economic growth, and bringing in these really interesting novel data sources, both through your randomized controlled trial as well as this new sensor data that you and Noah are collecting. I'd like to introduce Andrea again, who has been tracking the questions on YouTube and will I think maybe try to summarize some of them in one or two questions.
Yeah, thank you so much for that talk, Catherine. That was wonderful. There are two main questions. So the first is, was the community in Kenya asked about where they would like to see the funding be prioritized ever as part of the surveys?
Yeah, so were they asked, would you rather have healthcare or would you rather have, education? So economists tend to believe what are called revealed preferences more than stated preferences. So you worry that if you ask somebody, would you rather have education or electricity or healthcare, access to healthcare, that they'll tell the surveyor what they suspect the surveyor wants to know, that they won't give an accurate answer to that question, or that they'll be strategic in how they answer that question. And so that's why we've tended to rely on what we call revealed preferences. So if offered an electricity connection at a 70% discount, how many people took it up? And so I think, one indication that people didn't put a very high premium on the electricity connection is that even at this 70% discount, not very many people wanted to take it. Not very many people wanted to spend their, at that point it was about $130 for the connection. They didn't want to spend their $130 on the connection. They, by revealed preference, they're choosing to spend it on something else.
Gotcha. The second question is, after the connection to the grid, this was around like slide 19 in your slide deck, did you find out if these communities were provided electricity for all 24 hours of a day, 7 days a week? And the question comes from this background of how, like, for example, Nigeria, lots of households do not make use of supplied electricity because they can't tell which hour of the day or which week or month the electricity will actually be provided.
Yeah, that's a great question. So in some ways, Kenya is different from many parts of the emerging markets because they don't have load problems. They have, if anything, they have excess generation. So they have a reserve margin, it's upwards of near 50%. And so they don't have load shedding as happens in India, I know, in Nigeria. It happened in Ghana in a big way in kind of the 2015 timeframe. So in Kenya, that's not as much of a problem. But what we did see, and so with load shedding, you see kind of the episodic, like 6 to 10 hours out of the day, people don't have electricity. We did not see that in Kenya. What we did see, though, were extended outages. So I think 20% of our transformers did not have access to electricity at some point during our study. And when they didn't have access to electricity, that lasted for 3 months. And so basically what was happening is that the transformers were shorting or breaking, and then Kenya Power was not showing up to fix them for a long, long time. So I think that's a, one indication of why reliability might matter, that with very poor reliability, we're seeing these kind of poor outcomes in terms of the impacts of electricity on these households.
Thank you.
Thank you very much for your talk, Catherine. And thank you, Noah, for participating and backing up here. I'd like to take this opportunity to thank all of our speakers today for this first day of L4DC 2020. And I'd like to thank all our viewers on YouTube. We had a record number of viewers today, which is wonderful to see. And it's been wonderful to see the questions and the chat and the active discussion on YouTube. And just a reminder that for the contributed papers, there are open channels on Open Review. You can also access those through our website. So you can go online and ask questions and continue discussion. We'll have those going for the next 2 weeks. So with that, I'd like to conclude today's session and remind everyone that day 2 is tomorrow. We will be starting at 8:40 a.m. tomorrow with a 5-minute introduction, and then our next invited speaker will start at 8:45 a.m. tomorrow, Pacific time. So thank you again to all our speakers, and thanks to everyone for making this, this first day such a success.